Recording in progress.
All right, yeah, I mean, you can go ahead.
Okay, so I'm Yimeng Li. I'm from George Mason University. I'm here to present this paper, Uncertainty-Aware Proposal Segmentation for Unknown Object Detection. So the task we are interested in.
I think you have to mute yourself. Once again, yeah, I mean.
Yeah.
Yep, go ahead.
Thank you. So the task we are interested in is that in the autonomous driving setting, there is usually some unknown objects appear on the road and becomes a potential threat to safety. So for example, the vehicle might run into this big stone on the road and blocking the way. And so we want to have a detector system to detect these anomalies. And however, these anomalies are not included in the training data when you train an object detector or semantic segmentation model. So given an input image, we have a anomaly cargo box on the road, and given a regular semantic segmentation model, it predicts this cargo box as belongs to the war class, and we would like to have another image that highlight these anomalies in the original image size. So there are already some previous methods tackling this task. So in the ICCV 2019 paper, authored by Christoph, they propose this GAN method. So given an input image, you pass it through a semantic segmentation model, and then you use a generative model to synthesize the original image based on the predicted semantic labels. And the intuition here is that for the unknown objects or the out of distribution objects, like the cargo boxes, it's very difficult for the generative model to have good synthesis results. So here, if we have another model to compare the original image and the synthesized image, it's very easy to detect these unknown objects. And so instead of approaching this problem in a generative way, we approached it in a discriminative method way. So our idea is that we want to do uncertainty estimation. So given an object proposal, it contains one object, and and we try to classify this object into one of the known object categories. If the classification has a high uncertainty, then it shows that this object is an unknown object, one out of distribution object. So we design a 3-step method. In the first step, we extract object proposals and feature maps. So here in the example image, we extract an object proposal containing a cargo box. And then in the second step, we do proposal segmentation to generate an object mask on the object proposal. And given the object mask, we do proposal classification to try to classify the object into any known object categories. And if the uncertainty is high when we do classification, then it's an unknown object. So here, this cargo box has a high uncertainty classifying into either person, car, or bicycle. So it's an out of distribution object. So the proposal segmentation model takes in an object proposal and an associated feature map. And we train a proposal segmentation model to try to label each pixel of the proposal into one of the known object semantic categories and estimate its uncertainty. The output of the proposal segmentation model is an object mask. We threshold the pixels with high uncertainty on the background classes, and these pixels form the object mask because they have high uncertainty classified into the background categories. So they are potential object pixels. In the proposal classification model, we apply max pooling on the feature map associated with the object mask, and then we pass the resulting feature vector to a radial basis function network to do classification with uncertainty. So the radial basis function network, RBFN, is a distance-based classification and uncertainty estimation model. It computes the distance between the feature vector FUV and the centroid mu. And the closest centroid is the feature vector's class, and the distance between them denotes the uncertainty. So if the distance is very large, then that means this feature vector has a large distance to any known object categories. Then it's an unknown object or an out of distribution object. However, this RBFN network has some known problems. It is susceptible to feature collapse when we have multiple convolutional layers in the model. And it's also conflicted with batch normalization and gradient penalty. To resolve this problem, we propose this boundary regularization method, where we enforce a uniform distribution for the boundary pixels and maximize classification performance on the in-distribution pixels. So initially in the RBFN network, in the right figure, we have an unknown object package box. Initially, this RBFN network has the proposal segmentation model cannot generate a mask for it. But when we add this boundary regularization, when we train the model, we have a relatively high quality mask for the unknown object package box, and we can do further classification with it. So in the experiments, we set it up like this. The models are all trained with cityscapes dataset, and we evaluate it on lost and found, fishscapes, and road anomaly datasets. So lost and found and road anomaly are real datasets, while fishscapes is a synthesized dataset. Our objective is to detect the anomalous and out of distribution object pixels. We use 3 metrics to evaluate our models through OROC, average precision, and FPR95. So FPR95 is false positive rate at 95% true positive rate. We use it to deal with high imbalance situations. So this is a result on the proposal segmentation task. We compare our model with the GAN method, and so our model achieves better performance than the previous methods. It's even better than, it's also better than directly adding the RBF network after a regular semantic segmentation model. And this is the result on the whole image segmentation task. Our model is slightly behind the current state-of-the-art method, ring synthesized ++ model. So this ring synthesized ++ model is an improved version of the GAN framework. And our model performs slightly worse because even though we use object proposals, there are still some artifacts in the background which affects the result. So here we have some visualizations for the proposal segmentation results on a lost and found dataset. Our model is able to predict a relatively high quality mask across different kinds of objects and the various background. And for the whole image segmentation task, our result is on the rightmost column. So comparing to the existing methods, our model has significantly less artifacts on the background regions. And this is because we start from object proposals, which reduces the distraction from the background. We can also use our proposal classification mask to detect some mask RCN false predictions. So if here we have some results running mask RCN on road anomaly dataset images. Here we have a cow in the far distance, and it's predicted into truck with 98% by mask RCN. And however, if we run of the proposal classification model on the result, and we have a high uncertainty on the mask RCN predictions. And when the mask RCN prediction is correct, like here it predicts person with 100%, our proposal classification model also have very low uncertainty, only like 3% uncertainty for this prediction. So it's able to detect mask RCN false predictions. We also evaluate our models on indoor things other than just outdoor things. So we train the proposal segmentation model on AD20K dataset and evaluate on AVD dataset. AVD dataset is just a regular indoor thing datasets where it has some daily objects that not included in AD20K. So we have these serial boxes which are considered as unknown objects in the testing stage, and our proposal segmentation model is able to segment them out as an unknown object. We conclude that semantic segmentation model on detected object proposals significantly reduces distractions from the background, and using radial basis function network and the boundary constraint is well suited for uncertainty quantization task. And our model achieves competitive performance on multiple datasets and indoor things. And that's all of my presentation. Thank you for listening. Okay, so anyone have questions?
Thank you, Aiming. Any questions for Aiming? Any questions on Zoom? All right. Thank you so much for your talk.
Thank you.
All right. Carl, are you there?
Yeah, I'm here.
Hey. All right. So you can start sharing the screen.
Okay.
So our next invited talk is Carl Vondrick. He's an assistant professor in the Department of Computer Science at Columbia University. Before Columbia, Carl was a research scientist at Google AI. He completed his PhD in computer science from MIT in 2017. His research focuses on computer vision and machine learning. Other interests include sound and language, interpretable models, high-level reasoning, and perception for robotics. So let's welcome Carl to this workshop.
Okay, thanks very much for the introduction. I guess you can hear me okay?
Yep, we can.
Great. Okay. So sorry that I couldn't join in person. I hope that everyone in the conference and workshop has settled in your hotel rooms in Hawaii and they're all enjoying the views. But how much can you really trust your hotel room, right? Do you trust that room that you're in? Could someone have planted a microphone inside your hotel room and be listening to your conversations when you go home and talk, right? Could there be something in there spying on you in your hotel room? You don't know. You just showed up just a few days ago. There could be anything in that room, right? And so this is not just an academic problem, this question I'm posing you. In these remote work days, companies are putting microphones and cameras to monitor their workers. Police are placing microphones in rooms in order to snoop on lawyers as they talk. There's a potential of, with technology, and computer vision and audio processing all around us all the time, there could be a rogue camera or rogue microphone that's watching you without your knowledge. So, there's a couple of old school ways to try to fix this problem, right? You could, for example, turn on the TV really loud, right? And you could just turn on CNN or whatever your favorite news station is and just make it really loud. And that would probably make it very hard for any of these like rogue Alexas or rogue Siris or to listen to your conversation. That would also make useful conversation really hard, right? You couldn't, if TV's too loud, you couldn't talk with your friends. You would just, it'd be very annoying that the TV was very loud. There's some really interesting work done out of the University of Chicago just in the last few years that created the solution actually for trying to jam these microphones that can be spying on you. And they created this ultrasonic attack. So it is this bracelet that you can wear. It's shown here. The person on the right is wearing this bracelet. And it's making this ultrasonic sound that you yourself, your ears cannot hear. But it actually is able to jam any type of microphone that's nearby. And it leveraged some of the properties about how microphone hardware is built, assumptions that people who engineer microphones often make. It leverages some assumption of that in order to jam these. So if you have one of these, you should go home and turn one of these on, because you don't know, maybe in your hotel room there could be a microphone listening to you. But if you don't, right, and you probably don't, because this needs specialized hardware. Right? You got to have this really advanced hardware on your wrist in order to do this. And even this has been out for a few years now, so it's possible that someone that the people making hardware were able to build a defense into their hardware in order to fix this. So what can you do? How can you have some protection tonight, right? How can you go home to your hotel room tonight and sleep with confidence that, or talk with confidence that, hey, there's not some rogue microphone that's listening to you. So it's integrated across, as everyone knows, integrated into any type of sensing device now, whether it's a microphone or camera, is a neural net. Right? This is important for in computer vision and doing computational photography. Neural nets are being used. And whenever you use a microphone, there's a denoiser attached to it. These state-of-the-art systems are neural network based. And so there's this software that's integrated into all this hardware today. And so this is, we all know, it's kind of the focus of this workshop, right? We all know that these neural networks have these vulnerabilities. They have these problems. They're not robust to adversarial examples. They're not robust to the open world. They're not robust to the distribution changes. And most people in the field, we often view this vulnerability here as like a bug, right? We often view this is a problem. That's like the focus of the workshop, right? This is a problem that we need to go solve and build systems that are going to be robust. Two PhD students in my group, Mia and Chengri, are pictured here on the top up right. We've started to think about this and wonder, is this really a bug, or is this actually a feature, right? Can we view this vulnerability of these systems not as a bug that we need to be fixing, but actually as a feature that could potentially provide privacy? Maybe this is actually a good thing, right? We can actually use the fact actually systems are not fully accurate today in order to give us some sort of privacy, so that so you can go home and not worry about someone spying on you. You have control over whether a microphone is listening to your conversation or not. This idea is not, it's actually an old idea, especially in the written domain. This is basically an art project from 2010. This is a decade old now. And this was an art project where they designed adversarial haircuts and adversarial makeup that would disrupt any type of face detector at the time. This was disrupting the Yellow-Jones face detector at the time. This is before neural networks were popular in computer vision. And so you can go check out this website. It's a really fun website, cvdazzle.com. Has all these interesting ways to modify your appearance, modify your haircut, put makeup on your face that make it very difficult for the face detector in order to recognize you. This is, this somehow, if we think about kind of where the future is going with computer vision and audio processes being integrated everywhere, where's the privacy, right? Where's the privacy in the come from? Perhaps we need to start modifying our haircuts in order to get privacy. And so we've been wondering, could we actually do something similar for speech? Is there a way that we could take advantage of the vulnerability of these systems in order to create this adversarial haircut, this analogy of adversarial haircut, but do it for speech? Is there some way that we could build this system that could make these adversarial examples that are going to protect your speech, so that no rogue microphone could be eavesdropping on the conversation that you're having? So let's talk about what this type of setup here, just to dig in some of the details of how others might work. Let's suppose we have two different people in our system. We have Bob and Alice, and Bob is trying to talk to Alice. And Bob and Alice are friends, and they want to be talking to each other. Right? This is the conversation they want to be having inside their hotel room in Hawaii. But of course, there could be some microphone. You don't know. You never know, right? There could be a microphone listening in your hotel room. There could be a microphone listening to you right now, right? Just trying to listen to what your conversations are. There's always could be some, especially in today, there's always could be some rogue microphone being placed throughout you. So, we know, everyone knows about adversarial attacks. This is if you've come across neural networks, you've come across adversarial attacks at this point. So, it seems like it's pretty straightforward to build some defense here, right? Bob could take out his phone and program some adversarial attack on his phone, and have his phone speakers in order to play this adversarial attack. Make sure the attack is really low volume so that he can still talk to Alice, but still an adversarial attack nonetheless. And just, you can put his phone on the bed and play it. And because, modular reverberation, sound is approximately additive, right? These two sound waves will just be combined as he talks. Because it's low volume, Alice will be able to hear him. But because it's adversarial attack, any spy on microphone just won't work anymore. Well, let's go into some of the details here a little bit, right? Would this really work? Could you actually just use an adversarial attack just out of the box? Is that really the solution here that would give you a little bit of privacy tonight? Is that really what you want to be doing? And the problem is that in any realistic scenario here, it's going to be online. This is going to be, working in a stream, right? This is going to be an online problem. As you talk, the world is going to be changing, right? And that's going to change the characteristics of this adversarial attack. So if you just did your standard kind of baseline here of let's take your favorite way of producing adversarial attacks, and you program it on your phone and you apply it, the problem is that there's going to be a delay, right? There's this fundamental delay, and this delay is by the time you can play it, right? So if on the left, I start computing the adversarial attack from the box on the left, by the time I'm able to play it, the signal will have changed. And there's lots of reasons for this delay, right? Some are about the processing speed of the algorithm. The attack is not going to be instantaneous. It's going to take some time for the attack to be produced. That's going to create some delay. But more fundamentally, right, you're not going to be able to have produced the attack until you listen to the signal, right? And you basically need to see the entire signal in order to produce the attack. And so by the time you play it, even if your algorithm is instantaneous, very, very fast, and you program it in low-level CUDA, just make it really, really, really fast, right? There still would be a fundamental delay, causing whatever adversarial attack that you create on your input is not going to work in the future. And so there's going to be this delay. And so really, maybe artificial attack is not enough, right? In order to give you some privacy. What we've been investigating is that how we can build these predictive models that can anticipate what is going to happen. And I think this is a really important direction. It's the problem that my group has been working on for a long time in computer vision and other domains as well. How to anticipate what the future holds, right? I think this is really important because the world is always going to be changing, right? In order for machines to stay ahead, in order to stay relevant, we got to know what's going to happen next. And this is particularly true in the streaming environment. If you want to build this adversarial attack that's going to work online, it's going to work in real time, you don't care about the present. You actually don't care about the present, because the time you compute and process and do something, the world will change. And so what you fundamentally always care about is going to be what's going to happen in the future. So we've been developing this approach. This is a paper we just recently put up on archive. That basically build these real-time adversarial attacks that work on a stream. And we call this real-time camouflage. And the way this approach works is really simple, but it works so well that I just wanted to talk about it because it's very cool. Say here's a person speaking and you want to build some adversarial attack in the future. That's going to work on the future. So your observation here is going to be just XT on the left. But because we know the signal will change by the time we're able to play the attack, what we actually want to be attacking is the future represented by XT plus delta. And so we can just build up our model. We'll call this F theta here. This can be anything, there's lots of different things you can put there for the model. We use just a evolutional net operating on a spectrogram there. And so given xt in the past, it's going to be a neural net that's going to produce some attack vector in waveform space that can be played over the air on a speaker. And really the important point here is that because sound is going to be additive, that any rogue spy here and any rogue microphone that's listening to the conversation is going to receive the sum. It's going to receive the sum of xt plus delta plus at plus delta, and that's going to go into whatever this rogue, whatever the software system is operating on this. It could be a denoiser, it could be an automatic speech recognition system in order to produce the prediction line. And so this is actually really easy because we formulated this as this is a neural net. It's basically trying to predict what is the attack vector in the future that's going to work. We can just train in this. We can write down a loss function and optimize it to learn to produce an attack that will still be effective in the future. And so this is just to write this down, right? Is we say we want to find some parameter vector theta here, which is going to be making the attack not work and make the ASR model not work in the future, where your prediction here is just going to be the sum of what your model, your predictive model operating on the past, plus I actually get to hear in the future, which then gets sent to the ASR model the such to, subject to these usual constraints in adversarial robustness that you want the bound on the norm of this to be small. You want the attack to be small. Right? You don't want to change the signal too much. And so this is basically a predictive model, right? But rather than trying to predict something about the signal, so rather than trying to do a generative model, we're trying to predict what the person is going to say next, which is very hard. Right? It's very hard to actually anticipate the exact word I'm going to say next. This is an actually easier problem to optimize because we only need to find an attack vector that is going to corrupt whatever is going to be said in the future. It doesn't need to predict what the exact word I'm going to say. It just has to latch on to some characteristics about my voice, for example, and kind of hedge the bet about what the uncertainty is about the future. And just produce an attack that's going to work in the future. And from this, you can get real-time performance. at producing adversarial attacks. You can basically produce these attacks that work now on a string that is always going to be changing. And so, the lesson here is that this actually works much better than turning on the radio. If you're suspicious about a Rode microphone, you could turn on the radio, but it'd be much better to use this approach. It's going to corrupt the word error rate by 4 times more. It's kind of a big table in the paper showing off all the different results. Works in black box, works in white box settings, it works with and without defenses. And so I think the approach just works quite well at actually providing some sort of defense about, like, should someone be listening to you, right? Should you really want a microphone to be listening to your conversation all the time? And I think what's nice about this rule is that it's trained to have low volume. So it's, even though you can hear it, it's not loud, and so it doesn't disrupt your conversation. Here's a couple of examples. I'll play the attack next, but I just want to show you some examples. We got this to work in a realistic environment. Here, the photos you're seeing are our laboratory space out in New York. And so we're having real conversations inside this lab space. It's a kind of realistic room, right? And the 3 different columns here are showing, firstly, what the ASR model does when there's no attack, right? So you can see the ASR model works really well when there's no attack, right? It basically gets it right. So green means that it got transcription correct, red means that it got it wrong. If you play white noise, if that's what you do, and you're playing white noise with a certain amount of power, it doesn't really provide any type of a defense. But when you put this adversarial attack on, we actually predict what the attack vector is going to be. You actually can get very, you can maximize the transcription area here with much less power. So it actually has much less volume than if you just were to turn on the radio. Here's an example. I'll play I forgot to share my sound. Share computer sound. Here's an example I'll play of the attack in action. You're going to hear just the person speak normally with no attack first, and then it's going to play the attack. And the reason why there's going to be this delay is because it's predicting. Right? We can't actually predict an attack at the very beginning because there's some delay. There's always going to be some delay on this attack.
Now then, let's enter the city and enjoy the great feast that's being cooked. I'm nearly starved myself, for this conquering kingdoms is hard work.
So you can see, right, in the very beginning, right, it's transcription is correct, it's green, there's no attack, but the moment the attack starts, this word error rate just corrupts. One thing we found was that this works very well on many different types of words, right? We're not the first ones to be looking at real-time adversarial attacks, but most of the prior work has been very limited in scope in terms of the number of words they can attack, often just limited to just 10 words, for example. They use like a reinforcement learning-based approach, and so, anyways, this is an approach that I think it's quite straightforward, and it works really well. We've evaluated this on basically every word in the data set. This is hundreds, thousands of words, and generally attacks all of them. So this is a scatter plot showing what happens to the accuracy for each word before the attack, as well as after the attack. Each dot is a word, so any dot that's below the diagonal line here means that the attack was effective. Any dot above the diagonal line means that the attack actually was not effective, and it made it easier to recognize that word. So there's a few words that are like that, kind of as noticed. You can see all words are, most words are generally brought down. The size of the circle is showing how common that word is. So that really big circle on the top right is actually the word the, right? That's the most common word. And so what this shows actually is that this works best on the rare words. It doesn't work very well on very common words, but that's okay, right? The very common words have very low information content. You really want to guard what you're saying, right? You want to guard the most discriminative words, right? The words that have the most information content. And those are going to be the rare words. So there's this whole area, and this way the focus of this workshop is, how do you build these models that are going to be robust, right? This is, we've just showed a new type of attack. I think that, but how do you build these models that can be more robust to whether it be adversarial examples or there's some distribution shift in your environment? And traditionally, there's been quite a lot of focus in the community on trying to improve the training algorithm. So with neural nets, if you look at that adversarial robustness literature, tons of work going into trying to do adversarial training and doing vectorization inside the model. There's work that's analyzing the different types of tasks that you have, and there's very interesting work showing the correlation structure between tasks can intrinsically provide more robustness. So there is just intense focus on trying to improve these basically the training algorithms, right? What we've been looking at lately has been thinking, well, can we actually improve the testing algorithm instead, right? Is there some sort of structure? Can we improve what's going on the testing instead? And so I think everyone knows about self-supervised as learning. There's been tremendous just in the last few years. Just everyone's doing self-supervised learning. They're basically taking their data, splicing it up in interesting ways. And using that as a signal to learn, right? One of the most well-known examples is this kind of jigsaw puzzle here. This jigsaw puzzle, right, where you take the image and you break it up into pieces, and you have to train the model to predict where all the little pieces go. There's various extensions of this, and it's produce these really good representations for computer vision. But the signal's also been available at test too. And so we've been interested in this question of, can we actually leverage the structure here at testing time as well in order to improve robustness? So yeah, there's just tons of work in self-supervised learning, spatial context, temporal context, color context, audiovisual context, all this type of context that you can use. I should mention there's also robotics, right, being useful embodied, right? It's another type of self-supervised learning. There's all this really rich context actually in the world. And most of the not all, but most of the self-supervised learning field has been studying this at training time. But it's also there at test, right? So showing that one of my student my group found, it was pretty interesting, was that when you do an adversarial attack on an image, it not only corrupts like the task that you're trying to attack, but it also corrupts the self-supervised tasks. So there's kind of this collateral damage, right? If here's an image of a dog, you want your model to recognize that this is a dog. You can do an adversarial attack, find some noise that you put on top of it that makes this model no longer recognize that as a dog. This is a well-known result. But in the process of doing that, you've changed something else, right? And it turns out that you've also corrupted exactly the same these objectives for self-supervised learning. So this is a visualization in the middle here, right? In the original image on this, if you take one of these contrastive objectives, or it uses spatial crops in order to say, things that are cropped in the same image should be close together. On the original image, that objective is satisfied, right? Those two crops actually are going to be close together. But when you do this adversarial attack, when you find this attack vector, it collaterally also pushes this apart. And so this is a really interesting observation, I think, because it tells us two things. One is it provides a signal to detect when something has changed, right? Self-supervision will always be available at test time. It doesn't need the label. So it's going to tell you that something has changed, right? But it also, another thing it does is it also provides you a gradient, right? We can backprop through all of this, right? And we actually have a gradient now to actually say, how should I repair the image in order to reverse this attack? So in practice, we found that this actually does happen quite a lot. This is a histogram of images on ImageNet, showing what the contrastive loss is, basically, and then between when it's not attacked and when it is attacked. And the take-home point here is that when you use adversarial attack on a classification objective, it also shifts what this contrastive objective is, right? these two distributions are not the same, right? And so this means there is a signal here that in practice, these self-supervised objectives do provide a signal to detect when something has changed. And so we can use this signal not to just detect, but also as this gradient in order to create what we call reverse attacks. So traditionally in adversarial attacks, the attacker is trying to corrupt the image, right? We can kind of do a counterattack back in order to repair the image. And all this is possible because self-supervision is there at testing time. So the way this works, I think the algorithm is actually quite neat, and also some really interesting analytical properties. I'm going to discuss this next. But in order to motivate that, let me discuss the algorithm in a little bit more detail here, which is, let's first talk about what the attacker does. So the attacker, is given an image X, and the standard goal there is to find additive perturbation XA that's going to cause the classifier to be wrong. And so they would solve this optimization problem, find the attack here that's going to maximize the objective now, subject to some bound on how much this attack is allowed to change. Now, at testing time, if you want to try to defend against this type of attack or repair, right, what this type of change is, right? We can use this count under attack, but it's a little more tricky now because the attacker was able to use the original classification objective. They knew what the label was, and they were able to do it. When we're actually in a test time mode, we don't know what the label is, right? So we can't use the same thing. It'd be really easy if we could just flip the sign on that objective and build a reverse attack, right? But we can't do that because we don't know why. We don't know the label at test time. But instead, I think the ultimate critical tab, instead we actually know the self-supervised objective. And so we can find these reverse additive perturbations, which we call R, by minimizing the self-supervised objective. So try to find an additive perturbation that will fix the self-supervised objective. And if you can do this, then inference is really straightforward. It's just going to be, you just take your reverse vector R and add it to X and run your model F again. That will give you the predictions. Here's kind of a graphic of everything that I just explained. Here's the original image on the left. The classifier gets this right. It predicts the image that classifier predicts this is a Italian great A-hound. You take a state-of-the-art attack and you find the attack vector, you add to it, changes the prediction. It changes the prediction to be a whippet instead. If you do this reverse attack, but this reverse attack vector is actually shown here on the right, this is reversing not the original objective, actually the self-supervised objective now. And if you add that in, so you sum all these up, you're going to get the correct prediction back. One thing that's really interesting about this model is that we can show analytically that it strictly improves robustness. And I think that's actually really interesting about this, because we show that basically improves the worst case. It's actually really straightforward to see this. So here's kind of a sketch. The paper has an entire page devoted to this argument, but I want to give you just a sketch. It is really actually straightforward. So the assumption here, kind of in the worst case here, is that the attacker is going to know everything. It knows what your defense strategy is. It knows the parameters of your model. And you just assume the attacker basically knocks this at your head and it knows everything. So if an attacker wants to attack this type of model, the best thing for them to be doing is to be optimizing this multi-objective problem. They need to be optimizing two different objectives at the same time. So they need to be optimizing classification of objective. They need to be fooling our classification objective. But they also need to be fooling our self-supervised objective, right? They need to find an adversarial attack that's going to maximize the classification objective, but minimize the self-supervised objective. And this is what they have to do. If they want to bypass our attack, that's what the attacker must do. But this fundamentally creates a different type of problem, right? This creates a trade-off for the attacker. There's a trade-off between these two objectives. Which objective should they favor more? And so this actually creates a trade-off and here it's modulated by the scalar lambda, right? As you change that lambda, the coefficient there, you're going to be changing which objective the attacker is going to be trying to corrupt. And so it's actually really straightforward to see that this actually creates a lose-lose situation for the attacker, right? If they set lambda to 0, effectively ignoring our attack, well, we can just detect it, right, and still defend against it. But if they start cranking lambda up because they start wanting to favor the self-supervised objective more, attack that more, that's going to be reducing the amount of budget that they have in order for attacking the classification objective. So kind of fundamentally, this just improves the robustness, right, in the worst case. This is, I guess, what I like so much about adversarial examples is that it's kind of the worst case analysis about what could go wrong. And empirically, we actually see this is what happens as well. This is a plot showing the robust accuracy on the vertical axis versus what that lambda is on the horizontal axis. And so each curve here, so the two different colors are different types of robust models that have been trained to show two, just kind of show you that it generalizes across different models here. And so remember, from the attacker's perspective, they want to give you make the accuracy be the worst they possibly can be. And so what this curve shows, and we've theoretically showed before, but also empirically, the best thing for the attacker to do is actually just set lambda equal to 0, right? But then once they do that, we're able to defend against it. So our defense is shown in a solid line. Well, if you don't use the defense, that's shown in the dash line. And so you can see when you're operating towards lambda equals 0, turning on this type of defense using self-supervision at test time actually will increase your performance in the worst case. There's an interesting trend here on the right as well. We see these two curves that actually cross, right? So as the lambda term, right, as you start increasing the importance of the self-supervised term in this attack, it's true. Eventually, as you make lambda sufficiently large, the attacker is going to start corrupting the self-supervised objective, and that's why you see these curves start to cross, right? Because they actually make it so it's too hard, right? That they're saying that no matter what when they do such an attack, the self-supervised objective is still going to be small. But so even though relatively our defense is not effective when lambda is strong, there's no practical reason why someone would work there, because the absolute performance is still not as good as if they just set that lambda equals 0. So this is kind of the paper kind of has a more detailed explanation here, but hopefully that gives you kind of a sketch of why this defense actually is a really good idea. Using self-supervision at test time with this kind of adaptive procedure allows you to guarantee that the kind of natural structure in images is going to be respected in the model. So yeah, this got state-of-the-art results on many different data sets, including ImageNet. It's one exciting feature about this is actually compatible with existing models. You don't have to retrain them. Right? We actually don't have to train models in this work, right? We just are changing how you do evaluation, changing the procedure for inference by adding this constraint that must be respected. So I think I'm running out of time. So really three take-home points here, which is I think these predictive models are really interesting because they create these new opportunities for creating attacks, which I think can be good, right? Can be useful for privacy in today's world. But they also, as we saw in the later half of the talk, showed that they can be useful for defense too, right? You see these predictive models and self-supervised learning can create new types of defenses. And I think what's really interesting about those examples is that they really show you the worst case, right? I mean, they kind of are the worst case scenario. And so that provides interesting ways to do analysis and evaluation. Thanks so much for your time, and happy to take any questions.
Thanks a lot, Carl. Any questions from the audience? Yes. You'll have to come here.
So I have a question about the first part of your talk where you discussed the audio things.
Yeah.
So all the like experiments, are they for the single mic spy, or it can be an array too? Is the method robust against the beamforming techniques?
That's a great question. No, this is all with a single mic. Yeah, we've not experimented with whether someone uses beamforming or not. We have experimented with a couple of different kind of other defenses. Like we for example, we showed that if the spy here were to use a state-of-the-art denoiser, so you take a state-of-the-art system for denoising, our attack still is effective. But yeah, we haven't done anything with beamforming. That would be interesting.
Okay.
Any questions from the Zoom audience?
This is Terry. I have two questions. So the
Yeah.
first one, Carl, in the first part, and I don't follow adversarial audio stuff. So in the image space, we know that there are universal perturbations. If I know what your network is, I only need one perturbation. Do those exist in audio space? And is your predictive algorithm really just learning them indirectly, because that's an effective way to predict the future, is to have a universal adversarial?
Yeah, that's actually a good question. We did experiment with that. So it doesn't learn to do a universal attack. It learns to actually adapt to the characteristics of the speaker. It was very hard to analyze this. We didn't put this in the paper ultimately. We were wondering if this is adapting to like the tone of my voice, right? It adapts to a lower voice or a higher voice, right? But I guess more basic though, the reason why we don't think universal attacks would be effective is that it would be easy to subtract in audio, right? If you knew what the universal attack was, then the spy here could just subtract that, right, from the signal. So the advantage of actually having this predictive attack is that it is going to vary over time. So it's more difficult to defend against. Now, we haven't put these two projects together yet. We haven't tested whether this self-supervised defense, is able to defend against this type of predictive attack. That'd be an interesting follow-up for us.
Well, even for images, there's an infinite set of universal attacks. So it doesn't have to be, which one I use. I can choose among them, but I don't have to really know what your signal is. I can just, choose a random number, use that to drive my detector. So second question is actually related to the second part. So first, what kind of attacks were you using? Because if you're using an attack that matches the features, it's less obvious that the sort of self-supervision stuff will apply, because you get exactly the same features, as opposed to some sort of random noise attack or FPN or whatever that's really not worry about trying to match the features of the image.
Yeah. I don't know the answer to the question exactly. I think I'll refer you to the paper. My student Chengzi would know the answer to that. I can say that we evaluated this on a bunch of leaderboards, and it sort of got state of the art, got first place on a bunch of leaderboards. So if those models you're talking about are on the leaderboard, then I guess it's better than them. If not, I don't know.
So I know our attack is not on any of the leaderboards, because we didn't want to make it public.
Yeah. Okay. So yeah, you should put it on the leaderboard, and we can see.
All right. Thank you so much, Carl, for an amazing talk.
Thank you.
Hey, Stella.
Hi.
All right. Stella, you can start sharing your screen now. All right. So our next invited talk is by Stella Yu. She's the director of the ICSI Vision Group and a senior fellow with the Berkeley Institute for Data Science. She studies visual perception from multiple perspectives: human vision, computer vision, robotic vision, and artistic vision. She has developed new tools in spectral graph theory and machine learning to effectively uncover the relational structure of large-scale data. She has also pursued efficient representation and computation by learning from artists and exploring the connections between art and vision. Let's all welcome Stella.
Thank you. Thank you very much for having me. So today, I'm going to talk about some old work and some new work. And my title is Actionable Representation Learning for Open World Vision. Vision is such a wonderful sense for us because we have this completeness If you think about any other senses or measurements we can take in the world, it's only a piecemeal aspect of what we're experiencing. And we never even question the reality of the visual world. The visual world takes on life of its own. So all in all, I'm trying to approach that the effortless visual perception with the computational models that's driven by the natural data. One of the most important capabilities of visual perception is recognition. The dictionary definition of recognition is the identification of someone or something or person from previous encounters or knowledge. So there are really two aspects to recognition. One is previous encounters or knowledge. There's a knowledge extraction from what we have seen. And there's a comparison of the new data to the old data. So recognition is recognition. But if we reflect upon visual recognition, we seem to be able to talk about categories in isolation. For example, we can talk about dog categories by themselves, which means that we can see beyond the two types of variations. One is different instance of dogs and the different view variations of the dog. So if we want to be able to build a model for categorization, the model must have invariance. Whenever we take that view, we are focusing on what is a category? How can we go for invariant recognition? But when we come to model recognition, we tend to model it as classification. Recognition asks what identifies a category. When we model it as classification, that problem has changed. We can regard the classification as a two-level classification tree. The leaf nodes are the instances and the root nodes are the categories. The names, dogs, leopards don't really matter. It's the connection patterns that matter. So the connection pattern tells us what instances belong to what camp and what does not belong in the same camp. So it's such a common place to model recognition as classification, but in the process, we have performed a sleight of hands. We are focusing on how our category is different. Given all these images, so we know that classification is not recognition. Knowing how dogs are different from cats and fox may tell us how their tails, eyes are different, but doesn't tell us what dogs are. But as more and more categories come into this comparison, then the dogness will emerge. So the challenge in learning is that how can we achieve the same with the limited number of the classes and a limited number of the data? That has been the focus of my research. So I explicitly model recognition in this two-step process. One is doing knowledge extraction, the representation. Find the representation that can be useful for downstream tasks. For example, given this image, how can we extract similar images? One thing that does not require learning is just take the pixel values, the color values as is, as a signature of the image. And when we do retrieval by color similarity, there's no learning required and no labeling required. And we got the top row of results. And there, the images retrieved, sort of like the query, have the bright objects against the dark background, but it doesn't care about the semantics. It could be puppy, chef, cell phone, so on and so forth. So we wonder if we can do better than that. On the other hand, the other extreme of the spectrum, we train a model to recognize what each image contains with annotated data. We are told what each image is, a dog, cat. And we take that feature, learn it during the process, and then the nearest neighbor retrieval will reflect the same model in different poses. Our unsupervised representation approaches supervised classification. And if we are able to utilize the labels, our supervised representation can actually get better results than the usual baseline. For this example, the label for this image is dress. And you can see our retrievals pick out the nearest neighbors, focusing on the puffiness of the dress, doesn't care who wears the dress, how many people are wearing the dress. So how do we do it? For unsupervised representation learning, we don't have labels. We only have data, and we want to learn something about the representation. So in baby vision, we can't tell babies what a category is. Baby vision discriminates instances, not categories. It's trying to see whether the instance she interacts with are the same or different. That concept can be captured in the instance categorization task. In the downstream, when we have categorization, we can model it as two-level categorization tree. The roots are categories and the leaf nodes are the instances. If we don't know what the downstream task will be, we really could encounter any classification tree. So how can we prepare for that infinite possibilities during training time? One of the best things you can do is to do instance discrimination. You make sure each instance keeps alive in your representation, never collapse, because every categorization essentially is lumping some instances into one camp. So long as we keep each instance alive in the representation, the fine-tuning downstream will be able to get the categorization right. And this idea can be schematically illustrated as each instance wants to be different from every other instance. So, so the question is, why do we want to do unsupervised instance discrimination? Why is it better than supervised classification? Features representation learned from supervised learning. Supervised learning is great on the data sets trained on, but transfers poorly to in the real world. And for our unsupervised feature learning, here there are three curves. The black curve shows the training loss on ImageNet without labels, and it goes down by design. That's the objective training. The blue cyan curve is hypothetical, is a typical supervised classification test accuracy. It peaks as the training goes on, but will gradually drops, and that's commonly known as overfitting. But if you look at our 1,000 category test accuracy, we have no concept of category. So at the test time, we are subject to a test that we don't know at the training time. Training time, we only discriminate between 1.2 million instances. That test accuracy continues to climb. That is a fundamental distinction between unsupervised representation from supervised representation. It generalizes better. And our work has led to a set of approaches improving on different aspects of the algorithm. The next work we did was, now we can discriminate between instances, but how do we get to categorization? for the baby vision, essentially the baby needs to tell these two different instances are actually the same kind. That is a baby step, pun intended, for categorization. Instance discrimination is good for the representation it developed, but eventually we want to be able to group things and to see the commonality between different instances. So how do we do that? And this problem is faced not only by babies, but also in natural data, where the non-curated data will have correlated instances taken from slightly different views. We don't have the view tags. We don't have instant object tags. And from long tail distributed data where there's imbalance of head class instances and tail class instances. So our idea is simple. According to instance discrimination, each instance will repel every other instances indexed by different symbols, I and J. But there we can engineer one group of friends, xi and xi prime. These are the augmented version of xi. We know we want them to be in the same group. We want the feature to be similar. The goal is that given this known grouping of xi and x prime, we would like to find that xi and xj, two different instances, are actually similar, should actually belong together. So we capture this naturally similar instances by local feature grouping. So if you look at xi, xi is attracted to its friend, its Siamese twin. Xi primes a local centroid in the feature space and repels other local centroids. Because xi and j look alike, xj will likely to do the same. It will be attracted to this local centroid and repel the other. So if you switch back and forth, look at xi and xj's preferences, they attract and then repel similar centroids. And this property is going to put them in the same place in the embedding space. That's how xi and j is discovered to be in the same camp. Just with this simple idea, with this additional instance, so-called cross-level discrimination between instance and local groups, we are able to achieve SOTA, most notably with a very small compute on different sets of kinds of data, high correlation data, long tail data, standard benchmarks, transfer learning, semi-supervised learning. We have very small academic compute. This is something we are very proud to present the result on. We cannot win on compute. We can only win on the merit of the ideas. Next thing is supervised representation learning. The labels are hard to get by. What if we have them? Can we use them without losing the benefit of unsupervised learning? For example, what if we can have a coarsely supervised labels instead of these individual object levels? Maybe we can tell all different kinds of dogs belong to the super category of dogs, or cats and leopards and all that belong to feline. We have a follow-up work that build on the instance discrimination and seamlessly integrate with supervised learning, and that allows us to do subclass discovery. The idea is simply the following. We just need to revise that repulsion pattern slightly. Suppose these circled, shaded, and the color shaded areas are individual classes we have labels for. And from instance discrimination point of view, each instance is no longer repel everybody. It only repels instances belong in different categories. Noticeably, in the dog category, there may be two kinds of species of dog. And this dog instance is not gonna repel fellow dogs. And it only repel cats, for example. Likewise, for this dog, it will repel other category instances, not the same category instances. We want to maximize that discrimination. That's it. So what this criterion, so-called neighborhood component analysis, developed by somebody, by Sam Royce and all earlier, but we made it scalable through the memory bank and etc. You see, unlike softmax to try to find a prototype for the entire class, it allows subclasses to be at peace with each other. The representation can extend it in the within the class without conforming to a prototype. Yet between classes, the separation will be strong due to the class-wise instance discrimination. And these are the results we observed in the bottom row. Another aspect is that when we get to natural data learning, we have to handle the open long-tailed distribution of the data. The challenge is that a few major classes has a lot of instances, but majority of the classes only have few instances. And we also need to handle the uncertainty of the future incoming data that we have something that never encountered before. If you look at the tail end of the spectrum, for tail recognition, you want robustness. You want to generalize from small data. So something looks different, you should still be able to say, this is my tail class. It could be at odds with open set recognition because you need to be very sensitive. You want to say, this is something I have never seen. And the other challenge is that because we are focusing on the long tail end of the spectrum, we tend to compromise the performance on the head. And that is actually what encountered most in practice. So these three challenges are conflicting each other, and they have been studied in isolation with different methods. The problem is that they assume different training and testing distributions and settings, and methods developed for one camp does not work for the other two. In real world, the challenge is to handle them at the same time. When we worked on this, we proposed an idea with a memory and attention. It's illustrated here as the following. Let's say this is an instance from the tail end. It will activate some feature, it's direct image feature, but it will also activate memory with the head, body, and the tail. Different things you have seen that look similar in the head, body, and the tail. Now, these can be used to augment the direct feature. And we use the finite, let's say 5 instances in the training set to figure out which channels, which parts should be weighed more, so that the memory enhanced feature will help discriminate this instance from other categories in the set. And because we have a memory bank recording what we have seen during training, we can use we can test whether the new data falls within the distribution or at the end of the periphery of the distribution and characterize familiarity. I want to focus on imbalanced classification a little bit. If you think about it, it seems a very trivial problem. Some have a lot more instances, some have few instances. Seems like it's a number game. But actually the problem is much more fundamental. It's a diversity and coverage problem instead of a number game. If we come back to object categorization, how can we approach categorization with classification? We need to build up invariance. And when there are a lot of data covering the instance axis and a view variation axis, we can achieve this invariance. But if we only have few instances, the data is chipped away in both axes. Which set of images goes into the training set determines the performance. For example, if we take these, we might draw a different conclusion from a training set containing these 3 instances. For these have all dark colored dogs, you might reach the wrong conclusion that dogs tend to be dark skinned, and that will have very poor generalization, and the models come up with will also be unstable. So in closed world long tail recognition, how can we recognize something we rarely encounter? I liken this to rare disease diagnosis. If you have a rare disease, you go to a doctor and the doctor is ambivalent about the disease, what would you do? You seek second opinion. You go across the ocean and find another doctor. And if they reach agreement, you have certain confidence in the consensus. Otherwise, you might seek a third opinion. And the more diverse their training backgrounds are, the more confidence you have in their consensus. That's the idea of our approach. Except that we approach this problem through a principled bias, model bias and variance perspective. Compared to standard classifiers, existing long tail methods have some common problems. They gain accuracy on tail, but lose accuracy on head, which is this is rarely talked about in most papers. Secondly, it does reduce model bias on tail, but it increases model variance on head and tail. It's invariably, they always increase model variance, which means in plain language, it means that long tail methods are only more accurate on tail, but more volatile with varying training data. So our long tail method can reduce both bias and variance. It's a multi-expert model that is aware of the distribution of the training data. Next, we handled natural data, not unlike ImageNet, which tends to have objects right at the center. These are highly curated data, not only in terms of balancedness among classes, but also in the type of scenes it contains. In the real world scene, it has so much complexity. There are many objects in the scene: trees, curbs, pedestrians, lamps, so on and so forth. How can we learn from such complex scene data, learn a representation that's useful for object recognition? We extend the image instance-wise discrimination to pixel-wise discriminative feature learning. The idea is simple. We have a CNN learns a feature for every pixel. Based on the feature, we can do clustering. We can find a segmentation. Technically, we also make sure it observes the edge, low-level edge boundaries, but that's a minor detail. Now, instead of a whole image, we need to discriminate, like our earlier work on images. We have all these fragments, and we want the fragments to discriminate among each other. That doesn't require labels. And this whole process can be captured in a single clean formula solved by a two-step two-stage EM approach. What it leads to is that given set of images without any labels, the pixel level or image level, nothing at all. We are able to learn the feature. This is pseudo color visualization of the feature, the clustering in the feature space are prediction. And this is the ground truth, just for the sake of reference. And not only we can segment these images, but we can also discover these clusters of fragments. These correspond to semantics without names. For example, this could be hairpiece cluster. This could be faces, the torso, this could be helmets, wheels, so on and so forth. What is more interesting to me is that our discriminative feature learning can capture at the pixel level, it's a pixel to segment level contrastive learning, can capture the context. The feature not only tells the part it belongs to. For example, here's a pixel on the person. It also tells the features, also encodes the context this segment is embedded into. What we do is every pixel has a feature. When we have the segmentation, we can calculate the average feature for the segment. Now we can retrieve in the gallery the nearest neighbor of the segment feature. And you can see that, for example, this one is a bicycle rider. All the retrieved nearest neighbor retrievals reflect that. Here is a person, a back view of a motorcycle rider. Likewise, retrievals also have that. This is done for supervised learning, but during supervision, there's only two kinds of labels for a person. One is pedestrian, the other is rider. It does not differentiate bicycle rider, motorcycle rider, or horse riders. Yet we can learn that automatically. Here is a parked motorcycles. We know motorcycles, but we also know this is a motorcycle parked on a curbside, not motorcycle being ridden by someone. This contextual encoding is a very exciting aspect of pixel-wise feature learning. We have extended this idea to weakly supervised segmentation. Given images, if you have pixel-wise labeling, we can learn the supervised semantic segmentation. But there could be two kinds of weak supervision in terms of, say, coarse labeling, image tags or bounding boxes. Or another kind, the other kind is sparse supervision, point labeling or scribbles. These two camps are usually handled by different approaches. A class activation map for the coarse one, a CRF for the other one. But we use a single pixel to segment contrasting loss that unify all of them and deliver best performance in every camp. And the benefit is greater as the scribbles shrink their lengths to points. I want to talk about our newest work. For unsupervised representation learning, the current state is the hope for it. The practice at the moment is you learn some representation, and then you're hoping this representation will be useful for downstream tasks such as classification or segmentation or detection. So especially for segmentation, the task is different. You're learning from images, but you want to do pixel-wise labeling on segmentation. So all the representation learning is just a preparation. In the end, you have to do fine-tuning. Without fine-tuning, you cannot do anything. What we are targeting is that we want to do actionable representation learning. We have no downstream tuning. We can use it out of the box. That's our goal. That's the next stage of representation learning. Because I think this underlies our super fast performance of human vision. You can't wait till batch-wise learning at the downstream. So we, this is a poor man's illustration of videos. Instead of learning from a collection images, we do have work on that. But today I'm focusing on learning from collections videos. We want to be able to learn segmentation without any labels. So in the past, the way of thinking is that you have images, and we know that videos are sequence of images, and it provides optical flows. You have dense optical flows, a lot of long line of work on flows. And especially in connection with human vision. In human vision, there are areas processing edges, colors, and there's area processing movement, motion. So that seems to be resonating with our computational modeling. From the sequence of image, we can calculate the flows. And then given the two sources of the information, so here video seem to provide additional cue for us to derive segmentation. That's the goal. And that's how the usual approach. It's a bottom-up approach to segmentation. But we turn this around. Given these images, we want a factorization into segmentation, the one we want, as well as segment flows. We are looking at the output end. We go straight to this. We do not assume any idea about low-level visual computation. No edges, no flows are assumed. So how do we do this? First, we have a single image feature-based segmentation network. Given an image, it does pixel-wise softmax. So each pixel has to commit to one of these predefined channels. Each channel is, you can think of it as a soft segmentation mask. Simple enough. And there is a dual image. This model takes in two images, two frames, and it computes some dense flow feature. It's a feature, and then this thick volume is a correlation feature. Essentially is calculating the similarity between pixel in one image to every pixel in the other image. It's based on the PWC network, but we just use architecture. It's a very lightweight model. Based on this feature, we were able to come up with a 2D vector flow. And we use the segmentation mask, the soft waste, to calculate the average flow. And we are going to broadcast this, the average flow to every pixel within the segment. And so this gives us a composite segment flow. So essentially, we assume that everything belong to the same segment will have the same average flow. That's it. Now, this is a conjoined representation. In human vision, we always wonder, how do we solve the perceptual binding problem? This is our model of binding. We come up with a conjoined segment flow representation. Given the flow, this essentially says every pixel in J comes from certain displacement in image I. So we can use the flow to warp image I to reconstruct frame J. And then we can compare the two and use this loss to supervise the entire network. Okay, so in the entire model, the only knowledge we built in is this warping. It's a very simple warping, no network, no layer functions whatsoever. It just says if this pixel moves +1 along X direction plus I along Y direction, you just need to take that pixel from the other image and put it there. And then we compare. All this is just, we assign this meaning. We are hoping it will give us that, but nothing is built into it. This is the only loss we have. We never prescribe some edge extraction or texture feature representation or a flow calculation. Okay. So if we compare view synthesis, the traditional optic flow versus our segment flow, with optic flow, given two images, I and J, the optic flow is minimizing. This is also view synthesis, but it's solved in the pixel-wise manner. And the data X really could take anything. The flow could take any value. Sometimes people put a range on it. With the segment flow, we don't solve this discrepancy locally. We solve it over each image and over the collection of images. That's a global, and that we are solving the optimal solution in a coarse manner. And we assume the flow is piecewise constant. This is really the key insight of our work. We always assume the visual computation has to start somewhere. And it's so tantalizing to start with optical flows because we see it. It triggers our reaction, orient our eyes and all that. But instead of building up these low-level cues from local to global through grouping, we can get to mid-level segmentation and flows directly from a global to local through such a coarse organization, just piecewise constant, big pieces. So we train on YouTube US, it's about 5-second long videos on average and covering 94 categories. We test on 3 things: zero-shot object segmentation from single images, zero-shot moving object segmentation from videos. Here, meaning that we really apply the appearance model here, this pathway. Once the model is trained, we can apply to a single image and get segmentation. And for videos, since you give us a video, we can do further test time training on that video itself because there's no supervision required. And then last thing we did is on segmentation. There's a transfer learning for semantic segmentation. The key thing for the last is that we can outperform MoCo V2 without augmentation engineering. This is the first truly end-to-end zero-shot segmentation from videos. A lot of work claim they are unsupervised, but they always either assume a flow computation trained from synthetic data or something else from images. This one really has, other than the warping built-in, there's nothing. And what's so amazing is that if we look at, we pick 5 channels. So this is in the segmentation pathway, 1 column for 1 image. For this particular channel, you can see that it tends to pick out the objects. They're at each channel, it's picking out something. The key thing is that in the loss function, it doesn't favor any particular channel. It just says, together segmentation and all flows, they have to be in sync so that you can resynthesize the image. But when you train in this over the entire set, somehow there is one channel seem to pick out the general objectness. Just like when humans look at a moving object, it can segment it without knowing what it is. And these are the results we benchmarked on saliency data set. What's interesting is the first 2 columns results, they correspond to moving objects, right? Movable objects. And these are stationary objects like statue, plate, bench, rock, or some fixture. And for videos, we apply to Davis just to give you some qualitative idea about the results. And on the SegTrack V2 and FVMM, so these different data sets. And I will end. So I will just end with a slide summarizing the different aspects I touched upon. Learning without supervision, label supervision, how to handle open long tail distribution, how to learn from complex scene images and from videos. These are the aspects. I will let these are the video results to show, from our method, and this is a baseline which relies on optical flow. You can see the optical flow is really brittle, always has this unstable random things here and there. Thank you so much for your attention, and I'll be happy to take questions.
Thank you, Stella. Are there any questions from the audience? No. Are there any questions from the Zoom audience? Yes, Chris.
There's been some work recently with I think approaches like DNOW and other ones looking at the attention layers within the transformers that are trained completely without any label, showing that they are doing a decent job of something similar here with almost unsupervised segmentation, just with the attention layers. How does your work? Have you looked into any of those approaches with video, just to see if potentially the attention layers are actually doing this already?
Yeah, transform. So one of the comments we got on work is, PWC. We use a PWC network. It's a lightweight network. People adopted for optical flow. So maybe there's additional bias, but I don't think it's that important, because even earlier work with the FlowNet C, just take 2 frames in and output a flow. The problem is not as good. We can learn something. We build in certain bias in we choose particular architecture to facilitate learning. I think with the transformer, you need a lot more data, and you may get away with a lot of things, but and our data set is very small. It's only YouTube US data set. Some of the data, some methods are trained on vlog or some even larger data sets. But I think conceptually our method really assumes very little things. It's amazing we have not handled occlusion, for example. There are a lot of things we didn't handle. Just the simplest view synthesis criteria, yet it delivers the objectness. So that's very surprising to us. What may not come as people may not realize at the first reading is that, why would a particular channel shows it captures objectness from each image's point of view. The loss function doesn't encourage anything. So I think it's interplay between segmentation. You need the segmentation and the flow to be in sync. And combined with the data set. Data set certainly it's object-centered data set. But I think there's a lot of potential. There are still a lot of things we do not fully understand. But we are surprised, pleasantly surprised and amazed by the results. Transformer is a technicality of a separate dimension.
Thank you.
Thank you, Sarah.
Thank you.
Thank you for an amazing talk.
Bye.
All right. Next, we have a talk of one of our accepted papers. It's once again. It's by David Patrick and Michael Geyer on reconstructive training for real-world robustness and image classification. So, one second.
Oh, yeah. I tried to just share. You could you share. Yes. Not the screen, right? You just want that one. Yeah. That's what I thought we were doing.
Yeah, can you go one ahead? Can you just change your slide? Yep,
Okay,
you're good.
cool.
You're good. All right.
I can. Why do I see that? Yeah, why do we see that? We shouldn't see that. Is that good? I can't see why it's.
Are you sharing a screen or are you sharing a window?
It should just be the window, right?
Yep.
I don't see why it would do the screen. Maybe if I switch it and go back. It's this one. Fix it.
Oh, the screen is still positive.
Hold on, is it?
It's
Oh,
it's
yeah,
close,
you're
it's
right.
close.
No,
Nope,
see that?
nope.
I'm just have to do it without it. That's okay. I don't understand how-
All right, can you just I think we are good. Yep. Nope.
It's still showing up. I'll just have to do it without it, I guess.
All right. So sorry, guys.
Happens.
Yeah. All right. Take it forward.
Okay. All right. Hi, I'm David Patrick. I'm a PhD student at UTSA, and I'm here with my colleague, Michael Geyer, and we're going to present on reconstructive training for real-world robustness in regards to image classification. So it's no secret that if we want to get robust models, we need to be generalizable and not corruptible. And so we're going to show that through some reconstructive training that we can actually help our models be more generalizable and get rid of that through some various experiments. But before we do that, we should go over some background. So deep learning has made a lot of good advances with computer vision, including like automobiles, stuff like that. But the real question is, what about real world applications? Data in the real world is messy, out of context, or there's various corruptions that can occur. So these types of corruptions, we kind of categorize them into two things, which most people know about. The unintentional, those are weather, camera, those things that happen by accident, and then the intentional corruptions, which are adversarial attacks, trying to target the model. So we are going to focus on that, as attacks can be diverse in the way they attack and can be extremely complex. There's been multiple types of defenses. Oops. I think I accidentally did it. That was my bad. Okay, sorry. There has been multiple types of defenses. The first kind of category is the network modification. These are ones that try and change the model's architecture to accommodate for these types of corruption via some cleaning techniques inside of them. But they can be kind of expensive and require a whole new set of training. And then on the other side, we have input transformations. Those focus on cleaning the inputs before you feed them to the classification models. And these can be either static via like JPEG compression, bit depth reduction, or it can be learned defense scan. So that takes us to our motivation for when we were designing this is we had 3 goals in mind. We wanted a defense that would work on real world images. We also needed to make sure that the defense maintained the image quality going in and coming out. And defenses should be able to generalize to various types of corruptions and across models. So our proposed method, here's an overview of how we kind of train the network to understand these perturbations and reverse them. So I'm going to go step by step on each part, but this is just an overview. So the first part that we have is our generator architecture. It is a pretty standard autoencoder, but there's a couple small changes. The first is rather than having a skip connection on everything, we have one on just the last layer to help reconstruct the visual integrity of the image at the end. In addition, we use a low number of filters to help with creating a small bottleneck that will promote generalizability rather than overfitting. So this is the main cleaning mechanism for our images. And then this is the real meat of the training strategy. So our training strategy, what we do is we take the intentionally corrupt images and feed it in to the autoencoder or generator using the original image as the label, and it will go through and clean the image. After that, the image is sent to the target model, the generated one, and using the label is categorically classified. Once you do that, we take both the categorical loss of the target model, or the discriminator in this case, and the visual loss from the reconstruction era, and we back propagate that all the way through to the autoencoder. The hope is that we're focusing on 2 things. We want to focus on restoring the classification back to its original state, but we also want to make sure that the visual integrity of the image isn't compromised in any way. That way other applications can use it and we're not changing it. So in order to test that we did this effectively, we have 2 different experiments. The first experiment, we test how well do we defend against intentional corruptions. And to do that, we have 2 different models, or sorry, not 2 different models, 2 models that were trained. One was using FGSM data with a VGG19 discriminator, and the other one was using PGD data with VGG as the target discriminator as well. This is all in regards to ImageNet. So if you look at the table on the right, this is the top 1 classification accuracy. The important thing to note here is that the FGSM model was able to defend against the PGD and the deep full attack, despite never seeing those attacks. You can see there's a little star on the table of the FGSM. It would be an unfair comparison for FGSM to defend against itself since it's something it's seen. And we want to promote not being able to understand what type of attacks coming through. Same thing for PGD. It was able to defend against FGSM and deep full without knowing those types of attacks. We also tested it on no attack because you don't always know whether or not your image is attacked. We did see a slight degrade overall performance, but it is worth the cost on the other one. So numbers are nice and all, but like we said, one of the most important things is we wanted to show visually that we didn't change the image all that much. So here's all of the bunch of different defenses, and you can kind of see the layout. And our goal was to get back toward the original as well as we could. And you can kind of see in some other defenses, there's artifacts or color distortions that you really don't want, especially if you're transferring applications and other things. This is kind of a hard photo to see, so figured I'd zoom in a bit on one of the images. So if we kind of zoom in on the parrot right-hand corner, you can see all the different types. And our defense was able to clean around the beak, which is the most important part. And it has some artifacts in the background, but those are not nearly as important in the visual saliency of the thing. So that is kind of the first experiment that was run. So our second experiment, we kind of take these two different models that we've done before, where we have the FGSM model and the PGD, but rather than doing it only in regards to VGG19, we trained it using VGG19, and then we test time did a completely different model, in this case, Inception V3. The goal was, we wanted to see how well our defense generalized across models when the only thing it had to leverage was the data set. So everything else but the data set is different at training time versus testing time. So again, this is the top one. We do see an overall decrease on the thing, which is to be expected, as part of our thing is getting feedback from the model it was supposed to be defending. But it does show interesting things that it's actually able to leverage part of the data set in order to boost back the scores up. And we do outperform other defenses even doing this. So yeah. So kind of wrapping it up, our training strategy shows that it helps versus intentional corruptions. With the help of an autoencoder generator, we're able to maintain the visual integrity, kind of reusing it. We just demonstrated across multiple models and data attacks. But this is kind of just the surface. There's a lot more that you can do. We want to expand this to not only have non-adversarial, but those unintentional corruptions are as equally important as an intentional, as well as non-adversarial data sets. So yeah, I just wanted to thank the members of my lab and Dr. Fernandez, my advisor, who couldn't be here, for all the help in the project, and thank everyone for letting me have this talk. And the code is up on GitHub, so feel free to check it out. And yeah, questions.
Hence, that we found to be really caused by gradient mass constraints. Grades can reduce the gradient, so the effects can't work anymore. These simple effects. Did you test this with any attacks that are not subject to gradient mass?
That is something we're looking into doing. This was very wanted to focus on the gradient ones first, and then I want to extend it to not only those, but as well as those random not so gradient based attacks. We kind of cover that in the paper. So yeah.
Second question. So there are attacks that basically attack at feature level, so that the feature vector you get out.
Yes.
What would those do in your reconstruction model? Because you get a clean image out of it, it's very different.
That's an interesting question. Hopefully it should, the ones that attack the feature level, I don't know. That's a tough call to know exactly what would happen, but it's definitely an interesting experiment to look at. Trying to think off the top of my head what would happen.
Yeah, we haven't really performed that experiment. I don't even have any intuition as to what that would look like, so.
Yeah.
All right. Cool. No issues. Thank you so much, guys. All right.
Can you hear me?
Yes, I can. Just give me one sec.
Okay.
Can you start sharing your screen, please?
Okay. Is it full screen?
Yes, it is.
And now the slide changed?
Yes, it did.
Great.
All right. So our next talk is on towards unsupervised online domain adaptation for semantic segmentation. It's by Yevhen Kuznetsov. I'm sorry if I'm pronouncing the name wrong, but take it forward.
Okay. Hi, everyone. I'm Yevgen, and I'm presenting the work exploring unsupervised online domain adaptation for semantic segmentation. I'll start with some motivation. So semantic segmentation is an essential task for various industry fields, such as autonomous driving or robotics. Unfortunately, semantic segmentation models do not perform well under the conditions of domain shift, which is a change in the distribution between the sets of data a model was trained on or source domain and is deployed on or target domain. Such a difference in the data distribution can be caused, for instance, by transferring from synthetic to real domain, the variation of weather conditions, or even simply the location change. The goal of unsupervised domain adaptation, or later simply UDA, is to improve the model performance in the target domain by reducing the consequences of domain shift, but also without using target domain annotations. Most existing works explicitly align source and target domain distributions using adversarial learning or explore the use of self-training by iteratively refining pseudo-labels. Another interesting line of UDA research explores the use of proxy tasks as additional means of domain adaptation. One common limitation of existing semantic segmentation UDA algorithms is offline setting. They rely on curated target domain data to train the model for multiple epochs. Such offline setting introduces several restrictions. First, the need to acquire target domain data in advance. Second, model retraining is needed to benefit from new data available in target domain. And third, no adjustment to dynamically changing domain properties, such as weather conditions, is performed under closed-world assumption. These limitations make offline UDA impractical for many real-world applications desiring online capabilities. That is why we propose to adapt the model to new domain on the fly. Online UDA setting assumes that in order to adapt and produce predictions for a frame of a target domain video or stream, only source domain data or previous frames can be accessed. We chose to employ self-supervised structure from motion as a proxy task for our domain adaptation framework. First, we pre-trained the model in source domain with depth and semantics networks sharing an encoder. Then for each frame of the target domain video recorded by a moving camera, starting from third, the model is adapted as follows. First, a frame triplet or sample is constituted by the current and two preceding frames. Then this sample is stored in the replay buffer, which is empty in the beginning of adaptation. After this, several past samples are drawn, for instance, randomly from replay buffer to form a batch of image triplets together with the current sample. This batch is further used for model optimization. Utilizing past experience in such a way can be referred as experience replay. By making supervisory data distributed in a more IID-like way, it stabilizes the adaptation. It basically diminishes or prevents overfitting and catastrophic forgetting. After the triplet batch is constituted, the model infers depth, semantics, and ego motion with respect to the central frames of the triplets in the batch. When the inference is finished, image reconstruction loss is computed to optimize the shared depth semantics representation or encoder. This mechanism is widely used for learning monocular depth in self-supervised way. First, the synthetic views of the central frame are generated by warping its neighbors into it. The warping or reprojection through 3D space is performed using the respective depth and ego motion estimates. Then the loss can be computed as the difference between real and synthesized images. For more details about this procedure, please refer to MonoDepth 2 paper. In addition to geometric guidance, we regularize the predicted semantics in order to prevent learning more geometrically, but less semantically correct representations. For this, we first estimate the confidence region based on the predicted class probabilities for each pixel. This, for instance, can be done by using class adaptive probability threshold. Then confidence regularization loss is computed as the average entropy of pixels in the estimated confidence region. Finally, if the camera is not static, model parameters are optimized by minimizing the sum of computed losses. This condition is essential for geometry guidance to yield meaningful supervision. And then the described procedure is repeated for the next video frame and so on. This slide shows semantic segmentation results when transferring from a virtual kitty to real kitty. We make the following observations about the performance of our method. First, line adaptation significantly increases mean intersection over union compared to the non-adapted model. All components of our method contribute to this performance gain, but geometric guidance is clearly the key domain adaptation mechanism in our algorithm. Second, as shown in the chart titled Experience Replay, there is a positive correlation between a mean intersection over union and the number of past samples drawn from a replay buffer for each online adaptation step, which is represented by horizontal axis. Drawing past samples randomly yields higher performance gain than using several consequent preceding triplets. And the third observation is that our method is best deployed on longer videos, for instance, with more than 100 frames. The points in the bottom graph show the mean intersection over union difference, which is vertical coordinate, between our algorithm and the non-adapted model computed for video frames up till the timestamp represented by the point's horizontal coordinate. Apparently, the longer the model adapts, the more our method outperforms the non-adapted model, or at least till some limit. Despite this work mostly focusing on semantic segmentation UDA, the proposed method also naturally improves monocular depth estimation. Here we report depth estimation results on 4 widely used metrics, namely root mean square error, absolute relative error, squared relative error, and delta, as I call it. For all metrics except delta, lower numbers indicate better performance. and our algorithm outperforms the non-adapted model by a large margin on all metrics. What is interesting is that the addition of confidence regularization, which should mostly affect semantics, is also beneficial for depth estimation and slightly improves it on all metrics. We also show that our method generalizes to different scenarios. In particular, it performs well not only in simulated to real setup when adapting to Kitty or Cityscapes, but also greatly reduces the artifacts caused by deploying the model trained using sunny data in foggy or rainy weather. The video on the left shows how the model adapts to foggy environment, while the one on the right to rainy respectively. To conclude, despite achieving reasonably good results, this work is only the first step towards unsupervised online domain adaptation for semantic segmentation. And there are numerous possible directions to explore, such as handling small or infrequent objects, exploring various experience replay strategies, generalizing to other tasks such as panoptic segmentation or 3D bounding box generation. That's it. Thank you for attention.
Thank you so much for the talk. Hey, any questions? Any questions from the Zoom? All right, thank you so much.
Okay.
All right, so we will take a 10-minute break and we'll reconvene at 3 p.m. We have two more paper talks and one talk by Terence Poole. Thank you.
Testing, 1, 2.
Yep.
Perfect.
That's open.
Okay.
This one's plugged in. Yeah, it doesn't look like it has a little.
Yeah, it's got a little extra white on it.
Yep.
It's not focused.
Good call.
Bit better, I think.
Okay, so got this back. So interesting work, guys.
Thank you.
Having been bitten by the its gradient defense, sorry,
Oh,
it's
That's just.
I've got 2 papers where we thought we had good defenses, and then we were able to find different randomized attacks. Like SPA is probably the most aggressive and effective.
That's been the biggest struggle, is trying to figure out.
We did do some experiments with like VPDA and like white box attacks, and it just ends up going in a circle, right? Like when you have a trained defense and then you go at it with a white box attack, they just kind of circle each other forever, and we couldn't break out of that loop. So that was another problem. Yeah.
Hopefully we can eventually.
So I'm pretty sure that Art, Art, the adversarial research toolbox, whatever, out of IBM, they have a feature level attack. It's not the same as ours. It's not actually not as good, but we decided never to publish ours because it was too effective. So it was like, we didn't want to. Well, we published 2 papers on it, but we never, and we described it. It's actually not that hard to implement, but we did have a few tricks the student implemented that made it way more efficient and way more effective. And we didn't really want it to put out there, because
Right,
in terms of, well, one of our papers was on doing for face biometrics. We can attack face biometrics extremely well. We can make anyone's face anyone else's. Right? And use a human see nothing, but the computers are very sure it's Barack Obama or wherever you want it to be anytime you want. So, yeah, there's no, I mean, from an academic point of view, like releasing the code on that isn't going to help.
Right.
But I mean, ours are just way more efficient. So we do it in like 4 seconds, whereas if you use Fleet's work, the original feature level attack, it takes like 2 hours. Right? So you can't do anything.
It's not really practical.
It's not very practical, but being able to do it in a couple of seconds is. So with that, we were able to then attack things like we did all of ImageNet. We can map any ImageNet image to any ImageNet image.
Recording in progress.
That's why I asked about like, what is it reconstructed? Because we've thought about like the reconstruction attacks. It's like, well, if your features make it come back and it's so different from your original image, you might actually be able to detect some of them.
Right,
So,
exactly. That was a consideration, but we haven't done those experiments yet.
Yeah.
So I don't
I
know,
think,
but
they're separate losses, so I don't know how they interact.
really they're just completely separate models.
Yeah.
yeah, so I'm saying it's a separate model. So you might get something whereas over here it says this is like,
A dog.
a dog, when you, in fact, so because if we give you dog features,
Mhm.
your reconstruction network, your UNet or whatever it is, right, is effectively going to reconstruct something that's a doggish like image.
Should, yeah.
Yeah.
So
That's what I've been working on, trying to be able to track those features backwards. Because I've had such a difficult time understanding what comes out of my reconstruction sometimes, where I'm just like, that doesn't track with what I expect. There's like random times where like older versions of BGG or whatever, it just like everything came out in like pure blue and random stuff like that. So it's just like, I don't know how to do it, so I'm working
So
on
yeah,
it.
that's actually the reconstruction networks. When you get to full image net size, we also found that they were ineffective because there's so much in the image. Your reconstruction error is very large, even if you got the correct class.
Yeah.
Right, because it's like I could reconstruct the dog, but not the trees, the bush, the grass, and the water, and all of a sudden my reconstruction error is high. So that's the other part. It makes it
Yeah,
unclear how it would
we had
work.
to scale that properly with the other thing, with our bottleneck, and then we just like severely toned it down and used like a variation of PSNR.
It was quite like if you've toned it down enough, then it might be so. Even though it reconstructed a
Yeah.
cow instead of a dog, you might be like, hey, close enough, right?
Close enough, right?
It's got legs.
It's a really interesting space. It's super hard.
for me, the one thing I came away from, I've actually, we haven't done any papers. Oh, I once, one of my ex-students might, we still might do one more. I came away with saying, all it really showed me is we have no idea how deep networks work. That's really the only conclusion. Because
We don't know what we're doing.
there's no theory of how deep networks work for which adversarial images should exist. Like, you know, whenever it says this is how they work, it's like, no, I can show you that's not how they work. That's all. Other than that, I don't really know. You know, so from a practical point of view, I first I thought we'd learn a lot about how they really work, and then we kept doing it. It's like I'm not sure I learned anything. So.
I feel like over the time I learned less, even though I should be learning more.
So there's a certain like.
Hey, Sumit, can you hear me?
No less.
Yes.
Yeah, Pulkit.
You just like,
Pulkit, I could hear you.
10 more
All right,
questions.
can you start sharing your screen?
I don't understand.
Yeah, sure.
I keep thinking that adversarial attacks should be an.
Is it visible?
Thing,
It is.
Training
We'll
purposes.
start in like 5 minutes.
right? Because you would think like,
Sure,
oh, you
sure.
take this adversarial attack.
Yeah.
And it's pointing out the weaknesses of your model. Okay, let's use those weaknesses and do some adversarial training. But then that doesn't actually end up covering the holes because even one little tweak to the adversary, it's still, there's an infinite number of them.
Well, it's not infinite, but it's an extremely large, high-dimensional space.
Yes,
Right?
yeah.
But I mean, we actually had a paper like adversarial and hard positive. They actually can improve.
It does
You're not-
help, yeah.
But it saturates very quickly, right?
Mhm.
Games are far more effective at generating other training data
Right.
than that stuff does.
Yeah.
But yeah, the whole like the new attack, new defense, new attack, right?
So butterfly effect.
It's just kind of
My favorite.
We have one paper in archive that I might still want to follow up on, which is really trying to look at what is the cause and the solution. And the solution we have was actually very effective against everything except for these randomized attacks. But if the theory was right, then the randomized attacks still wouldn't work. So it's like, I don't know.
yeah.
Randomized attacks are, they're not fun to deal with.
Nor fun to experiment with because when we ran them, they took 6 GPUs, or a machine with 6 GPUs. They took a month and a half to run.
Yeah, that is.
And then it's like, okay, that didn't work. Now what? And then it's like your iteration cycle gets really slow when they're.
Yeah, that's one thing I've been really annoyed with. Some of the attacks and defenses are unreasonable in the hardware that is required to.
Yeah, it's not like everybody has access to that.
Like a
Yeah.
TPU storage facility of whatever. So,
And a lot of the reason people are using things still like CFAR is because not everybody has access to this big hardware, but then a lot of attacks and defenses don't see it.
Hello, Sumit.
Yeah, Pulkit.
Yeah. So we have lost a few audience, but I think we are running short on time, so you can go ahead.
Sure.
All right, just give me 1 second. Hey everyone, our next talk is an accepted paper talk. It's by Sumit Kumar and Badri Patro. The title of the talk is Auto QA the question is not only what, but also where. Take it ahead, Sumit.
Oh, sure. Hello, everyone. I, Sumit Kumar, I am going to present work titled Utopia. The question is not only what, but also where. Along with myself, authors of paper are Badri Patro and Vinay P. Nambudri. For this paper, we get inspiration from VQA task. VQA is an interesting task as it analyzes ability of AI agent to answer wide variety of questions. We aim to investigate and evaluate its efficacy in terms of localization-based question answering. We did this in the context of autonomous driving, where this functionality is important. So can we have a multimodal data set consisting of several image view and LiDAR point cloud data as input, and where we could use all this information to answer question? Also, one more important question we had that, can we address the important task of able to answer question related to localization ability, which is important in field of autonomous driving. Now, both these aspects are crucial if we are interested in broadening the capability of visual question answering to the practical relevant scenario. Now, consider the situation if an AI agent failed to answer the question whether there is a pedestrian to my left, can we trust its ability to drive safely? Motivated by this aim, we embark on a novel question answering challenge that we termed AutoQA. As shown in figure, the question is not about what is around me. It is about whether it is present in a specified direction. This is specifically designed to test the localization ability. Our new multimodal dataset, AutoQA, is built over all-purpose dataset. As shown in the figure, our dataset consists of 7 images corresponding to the 7 different directions around the reference vehicle. As we can see in the left figure, the 7 different directions are front left, center, front right, side left, side right, rear left, and rear right. Corresponding to these 7 images, we have LiDAR point cloud data, which is taken using the LiDAR sensor, which has a range of about 200 meters, and it produces approximately 1 lakh point. And in the figure to the right, we could see that the point cloud data give the 360-degree visual space around the reference vehicle. Also, the 3D bounding box present in the ArgoVerse dataset are used to generate question answer pair. So considering all these images and the LiDAR point cloud data and the 3D bounded box, we have generated 3 different types of question, namely the exist type of question, count, and the closest type of question. For example, consider the first question: is there a pedestrian to my side right? It is an exist type of question. Similarly, we have other type of question, like what is the count of vehicle on my rear left, which belongs to the count family, and some other question belonging to the closest type of family. In the next few slides, we will briefly summarize about different aspects of our data set. We have around 210K question answer distributed in training, test, and validation data set. For question answer generation, we use functional program For example, consider the closest type of question: what is the nearest object to my side left? So this question could be generated using the template or the functional program filter underscore unique followed by a relate filter and followed by a closest filter. From the figure 1, we can see that all questions are almost equally distributed among different families, with approximately 37%, 21%, and the 41% share of each family. Figure to represent how distribution of question varies among the direction. We can infer that there is no skewness toward any direction in our data set. Similarly, the third pie chart describe how object entities for which questions are distributed in a 360-degree visual space around the reference vehicle. We can see that in our data set, objects are not concentrated in a specific direction, which prevent any bias exploit by the answering model. Yeah, this is a sample JSON taken out from our data set. Each object in this JSON consists of family index representing to which question it belongs, its answer, corresponding LiDAR image index, template, which template is used to generate this question, details about the video file from which image is sampled, and details in which split this question like. Yeah, in order to solve this task, we appropriate baseline are tested by us. Now, so we tested two different type of model and followed by a combination model to solve this challenge. So for image only model, we used hierarchical attention over images. As you can see in the figure, the level 1 attention, we experimented with different existing attention model of visual question answering. So we got maximum accuracy of our 73.1% with mutant based model as our level 1 attention. Similarly, just like CNN for images, PointNet++ is used in the replacement of LiDAR only model. We have used both single scale and multi-scale grouping for leveraging feature vector for the answering model. As we can infer from the table, we got maximum accuracy of around 56.5% with only LiDAR modality. In the combination model, we took advantage of both LiDAR and image-based model. We laid out two pipeline, one which is similar to image-based model and second pipeline which is similar to the LiDAR-based model. And with the combination model, we got maximum accuracy of around 74.8% with the combination model. Finally, we evaluate the efficiency, its localization ability. Yeah. Each question in our data set is associated with some direction. To test whether a model focus on correct image, we test its performance. So these are some results from our data set. In first example, model is asked about the count on the front left. Similarly, in the second example, question is about whether the obstacle is in rear left direction. And similarly, in the third example, question is about whether which object is closer to my rear right. Finally, I would like to conclude that through this work, we introduced a novel semantic challenge AutoCAD that aims to evaluate the functional aspect of ability to localize accurately while answering question. Moreover, our work includes the practical aspect of answering question by incorporating all the views and the point cloud data that are available for answering the question. This enables us to consider various aspects of the task, that is, to what extent an image-based approach alone able to solve the task, and whether the image-based approach able to attend appropriately to the right image while answering the question. Our analysis also shows that incorporating image and point cloud information perform marginally better as a baseline. Also, we could analyze failure modes for this task to empirically evaluate the autonomous driving ability of AI agent. Yeah, that's it. Detailed explanation about question generation, dataset attribute, and the experimental baseline can be found in our paper. Thanks to all of you. Have a nice day. Questions?
Thanks a lot, Samir. Are there any questions?
Yeah. Am I audible?
Yeah, I could hear you.
Yeah. So one question about the data set, like why isn't there like 8 images instead of why is there 7? Like why is
okay,
the
so
image...
okay, so the data set which we have used to build this data set is the Orgovas data set. So in Orgovas data set, for at a given point there are 7 views of a object for images. That's why we have taken the 7 different views around the reference.
It was shown for that car, right? Autonomous car, and I was like surprised why they haven't kept something in the back too.
Yeah, so like the way these data sets are taken are like they mounted a camera overhead and then they capture the multiple view at the same time. So in the data set that we had used to build had 7 views. So yeah.
And so in your model, when you're feeding all the, so you are feeding all the 7 images with the question to the model, right? Simultaneously.
Yes. Yes. So in image
So-
based mode.
Yeah. So and so when the attention is applied, the attention is applied across all the 7 images and the text.
Yes. So like the idea was in the hierarchical based attention model was to first level attention should attend to the object, and the second level attention should attend to the right direction.
Okay. Okay. Thank you.
Are there any more questions? All right. Sumit, you have one more paper, right?
I think Vivek will be presenting it.
All right, cool. Vivek, can you start sharing your screen, please?
Sure. I think I need to give some permissions. Just
Are there any permission issues?
yeah. So I think I have to rejoin. Just a minute. Yeah.
All right, sure. Vivek, did it work? Can you unmute yourself? Hello.
Hello.
Yeah, perfect.
Yeah.
All right. So our next speaker is Vivek Gupta. He's going to talk about VQuad, video question answering diagnostic dataset. Take it away, Vivek.
Yeah. Hello, everyone. Myself, Vivek Gupta, and I'm going to present VQuad, video question answering diagnostic dataset. So apart from myself, the author of this paper are Badri and Patro, Hemant Parihar, and Vinay P. Nambudri. So about video question answering diagnostic dataset, this is a synthetic dataset which is primarily designed to evaluate video-based question answering techniques. So it contains synthetic objects in the scenes, and each object is associated with some object properties, as well as some of the relational aspects as well. So so a sample of the object with their properties are mentioned. So on the left side, we have the objects with the shiny aspect, which we call as a metal variant. And on the right side, we have all the objects with the non-shiny aspects, which we call as rubber variants. So for each object, we have a texture associated with them. We have a shape associated, and we also have size. So in front, you can see lined up the small objects, and on the back, we have all the large objects. So the texture is added because we also have the movement associated with each of the objects. So to capture the movement, we have added texture. So the movement can be like jumping, which is where the object moves up vertically and comes down. and there's a rotation involved. So to capture rotation in sphere and cylinder, we have added texture, and we also have a movement type, and there can also be a no movement involved with any of the objects. So we call them as still object. So these are the object variants in our data set. So a brief overview of all the object properties which will be there in our data set. So so this material, texture, shape, movement, color. So colors will be among the pairs, since we are using texture containing two colors. So there will be speed involved. The objects will be moving fast or slow, or they can be rotating fast or slow. And there is size involved with each object, small and large, and the relationship. So an object can be on the left side of another object, or the right side, or behind or in front. Now, so we have generated questions based on all the specific properties of the objects. So the relate object building block tells us if the object is on the left side or right side. So the question filters applies these small modules to each of the objects, and it filters out another subset of objects. So the question returning the containing the last the last module of the question defines the question type. What is going to be the question type? So we'll see the example in the next slide. So there is relate, which tells filters out all the objects on the left or right. So there is a count question building block, which counts the number of how many objects are there in the set. The exist type checks if the object with a specific property exists or not. The same compares the objects and returns all the objects with the similar object attribute value. The query object returns what is the object attribute in the question, and filter specific filters out all the objects with the specified object property value, and gives the set of remaining objects. So the filters is different from filter specific, which selects a range of different filter specifics. So filters contains a set of filter specifics value, and it applies multiple filters, and it gives it returns the set. This is added to generate the variety in questions. And the compare attribute compares the value of the objects, and then returns yes or no. So so here is the example of a sample video generated. So we have this big moving striped blue and green rubber cylinder in front. So so we define the object types as only fast and slow, so that like the slow object will move in small amount, and the large object will move to a greater distance in the same scene. So on the right side, we can see the type of question we'll be having. So the question is asked, what is the movement rate of small red and green thing? So we have this answer as slow, and small red and green thing, there is only one small and red and green thing, so which is the cube, which is so red and green thing. So okay, yeah, so which is in the behind, we can see bubbled cube going on the back. So it's that. So the last thing is like last block which is used to generate this question is query speed. So which is trying to query what is the speed of the what is the speed of the object in the question. So so the only object which remains in the set is a small red and green cube at the back. So it's trying to query that. So it returns slow. So this is a different type of questions being produced with the template. Another set of examples we have is here we have this big jumping bubbled brown and gray metal cylinder. So in front we have this jumping object. We can compare the jumping type with the sphere beside the cylinder. So we can see the fast jumping cylinder is moving more up than the slow moving cylinder. So there again, we have different question types based on what type of question it is asking. So we have some more examples from our data set based on the question type for each one. So here also we see the question type of equal material. So here the question compares the material of the two objects. So query shape is basically trying to find the shape of the object, is asking about what is the shape of the mentioned object. And each object is identified by mentioning all of its properties. Like big jumping bubble, brown and gray rubber cylinder is one of the property. Now we try to obtain object maps, attention maps for the different models we tried. So one of them is sequence to video text, where we feed in all the frames of the videos, and we try to then we feed the question. Then we feed the question, and we try to find out like where it is attending where the question is being attended by the model. So here are some of the good attention maps we have obtained for each of the question. Like, are there any small red and green things in front of rotating bubble red and green thing? So it is trying to focus on the different objects and then try to answer the question. And some of the bad feature maps which we obtained were for some of the very complex questions. So when we ask if this object is expected to hit the other object, then the model seems confused, and we obtained a bad feature. So yeah. Thank you. Any questions?
Thanks a lot, Vivek. Any questions from the audience? Any questions on Zoom? All right. Thank you so much, Vivek. All right, so we have come to the last talk of our workshop, and it's an invited talk by Terence Bode and Mohsen Jafarzadeh. So Terence Bode is the L. Pomar Endowed Professor of Innovation and Security at University of Colorado, Colorado Springs, and the co-founder and CTO of Securix Inc. Dr. Bode runs the Vision and Security Technology Labs, machine learning, computer vision, surveillance, biometrics, and general projects in computer vision. He received his PhD in computer science in 1986 from Columbia University, and then spent 6 years as an assistant professor, and 2 years as an associate professor at Columbia's CS department. Mohsin Zafarzadeh is a research associate at El Poma Institute of Innovation and Commercialization at the University of Colorado Springs, Colorado Springs. He did his PhD in electrical engineering from University of Texas at Dallas. Let's all welcome Terence and Mohsin. All right, are you okay? Oh, you want?
Okay.
Yep. You can just let's see, you're sharing the entire screen. Where is it?
Maybe because the bar.
Oh, that should be the case.
No, I was going to cut off the slide, lots of slides.
All right. Nope. I have no idea. Can you just go one forward and one back?
Can people on Zoom see the top of the slide?
Oh, 1 second. I know what to do. Can you shift this somehow? Yeah. It's somehow cutting down.
Well, it'll be a novel talk. We'll be missing parts of it. Have to fill in the blanks.
Yep.
Find something.
Maybe. No?
1920, but then-
Nope.
Okay.
All right, sure.
well,
Okay.
Okay, so as you said in the introduction, I'm Terry Bowles. I've been doing the slide better learning. So I always think a good talk should have a bit of a surprise in it. So I've actually added 2 words to my title.
Can
Okay, so I'm not going to repeat the introduction. So I'm Terry Bolt. I'm going to talk about learn without labels. Okay, so a long time ago, this is actually from the slides from my students' presentation at CDPR 2015, which is when we first had our first paper on open world learning and gave a very formal definition. In the traditional multi-class system, right? I'm going to make this guy go away. So, you know, we have our traditional classes. So this is all back Caltech type data set. You have the classes of interest. Other things can come along. So out in the real world, new objects exist. They actually come into existence every day. I might want to have a new category for them. I might want to have to deal with things I've not actually labeled, but I got to reject.
And there might be other classes I have to learn. And so we first defined back in like 2012, 2010 timeframe, open set, which I'll get to in just a second. So when we talk about closed set versus open world, to us, the open world is defined by the characteristic that, and this is from, again, from our original paper, where we have to detect things as unknown, right? That's to us, the rejection of unknowns, right? But then we have to basically somehow label them and then incrementally learn them. And that's what the distinction between open set and open world comes down to. So in a closed set problem, everything, the boundaries are closed. All the sets in a mathematical sense are formally closed. They have a boundary that the next thing comes right up to, and they partition the world. And a problem with that is if I sort of scale up my world, there's a whole bunch of it I did not actually have any data about, but I have just labeled because I made a partition. And when I draw those hyperplanes, my in this case, a simpler SVM-like model, or in my, the top of my deep network, those planes go on forever. No matter what you've done, you've labeled Mars. I don't know what side of your plane it's on, but Mars is there someplace, right? So you've labeled everything there. I don't know what species it is, but and even in the smaller world, right? There's often places like the bottom corner here where there is no data, and I really have no business labeling stuff far from what I learned. So that's when we defined open set. We really, and a number of people have been talking about open set, right? It is not simply rejecting unknowns. Recognition with rejection goes back to the 60s, before maybe anyone in this room was born, even before I was born. It's older than us. And open set is about more than that. It's not just with rejection. I'll get more formal in a second. I want to be able to define the boundaries of those classes, but they're sort of open, right? I don't know how close the world will get to me, so I want to be a little careful about them. But in the open world, I have to detect those unknown things and learn them. I got to learn about my new world, and that's what makes it an open world. My world is now a set that keeps growing, as opposed to open set, where the things I've defined and know about have things that are close to them, but that set doesn't change. So in this case, it's open world. Lots of people keep talking about open world in long tails, and the natural world is, sorry, so in the open world, I have to add this new gold thing down here that I hadn't seen before. The natural world is both open and long-tailed, but it doesn't, the open world does not have to be long-tailed, right? I can be a product manufacturer, or I can be Amazon, right? And I don't really care. New products come in, I want to put them on my data site. I don't care about everything in the world. I care about a subset of the world. And the world's long tail is also very odd. It doesn't get talked about very often, but the long tail of the world, if I'm a scuba diver, is very different than if I'm hunting in a safari, right? What I see and the frequency with which I see it depends on where I am and what world I'm in. So it's not even like there's one long tail. Everyone's got their own tails with the long world. It's a very messy problem. And you can study long tails. That's a great problem, but it's not what I'm going to talk about. So in our original paper, just because I want to talk a little bit about some of the flaws we had, I could point out our own mistakes. We had some nice things. We formalized the problem. We gave an algorithm. We had something advanced and state of the art. We have some nice theorems for how to build formally open space risk or formally bounded open space risk stuff, which I'll get to a little bit more in a second. So basically, we had some composition theorems that let you prove things are provably open set, bounding open space risk. But the paper in our first papers had a fundamental flaw. And unfortunately, our next work on that space continued, and a few other papers have followed on. We defined the problem as you're supposed to recognize the unknowns and then label them and then learn them. Unfortunately, our protocol and everything that's come across since then detected things as unknowns, but then it gave all the new incremental classes labels, whether or not you detected them. All right. And so it made the protocol much simpler, but it really was a combination of open set and incremental learning. You always got all the labels, whether or not you detected them. And we'll come back to why that's more complicated in a second, but that was a fundamental flaw. So now I'm going to talk a little bit about open space risk and open set risk and why I think they're actually still important. And then I'll show you why maybe they're not as important anymore, but they're still important to understand what's going on. Well, if I talk about open space, it's all this space that's far away from the things I know. Okay. And there's a risk of labeling it. When I label what kind of life it is on Mars, I've probably got it wrong. Right? It's too far from anything I've sampled. I don't belong labeling stuff there. Okay. And so we define this idea of open space risk. I can think of the space around where I've labeled data, and then can put a big sphere around it for everything else, and I can make that sphere grow. And then I can look at the ratio of how much space have I actually labeled divided by the total volume of the sphere. And if I've labeled too much of it, then I've got a lot of open space risk. And if I just take planar classifiers, I will label all of it. And so my open space risk, right, is not good, right? It's not bounded because I keeps growing to infinity, right? As the ratio is bounded, but the top part, right, keeps going to infinity, and the bottom, which is the stuff I actually know, right, doesn't. So I get a problem. So in our first paper on what is open set recognition, we wanted to balance two things: the open set risk and the risk, empirical risk for the known classes. And if I just want to do recognition with rejection, all I really have done is converted my K class problem into a K+1 class problem, and I don't need any of this formality. The problem is it doesn't account for how much of the space can be open in the open set risk sets. So we don't normally account for that. So it's not quite just deal with rejection. You want to balance these risks. And very few people are worrying about this anymore. And one of the reasons is because no one thinks they have to. Well, now we actually, in this paper, we actually end up proving that you don't really have to worry about as much as you used to, because if I work in deep feature space, as opposed to hand-tuned feature space, the feature space always supports a bounded, not necessarily best. So the trade-off is still there, but the open space risk can always be easily bounded, in part because almost everyone does deep feature spaces using L2 normalization on the side. So what you end up doing is you crush your feature space. It lives in a sphere. It's not a huge sphere. And you can basically say, if I'm outside the sphere, the biggest sphere I've ever seen in training, then I'm not from your world, right? So you can easily just add a little bit to your classifier and make it not very deep, but it was nice to add a little bit of formality to this. Being able to basically measure distances and then still reject stuff from some origin to your more space or whatever makes it a little bit easier. And then you can prove you have bounded open space risk. It doesn't prove you balance the two, but at least it's not infinite, so you can get there. It's not true if you don't add the extra little steps to classify, but it's true. So now I want to talk about generalizing to open world learning without labels, right? Which was a problem I didn't really want to work on, but I was forced to by DARPA, so I'll work on it. And then we found some interesting things along the way. So there's some interesting insights that I think will translate outside of our problem to those of you looking at other open world problems. So this was our original figure. And of course, if I don't actually get labels, then I'm going to do something else, and I'm going to use what everyone else naturally is going to do. Is I'm going to cluster, and I'm going to use my cluster labels as my labels. I'll call them quasi-labels to separate them, because we'll talk about real labels. So now I've got labels, and we thought this was it. We just put it together, and it did not work. Did not work at all. And I will come back to it. To get effective open world learning without labels, you actually have to add something that's going to manage your uncertainty about those cluster labels, the quality of the cluster labels, and use that to manage when it's finally time to learn. Because given any subset of data, I can always cluster it. That doesn't mean the clusters have meaning. If I really want to do effective learning without labels, I hope to actually learn something with meaning. Then I got to have something that decides that the clusters have meaning. If I say I use K means, right, I will always get K clusters. That doesn't mean they're good clusters. It doesn't mean, right, I have something else we're going to have to add to it. So the critical issues to be resolved to do open world learning without labels are, we're going to need a better protocol. I'll talk about that next. I'm going to adjust some clustering things. So one of the other problems with clustering is, if I know how many clusters I want to have, I can do it. It's easy, K means. What do I do when I have data and I don't know how many clusters they are? I don't really have the right to assume that the clusters are balanced in any meaningful way, because in the open world, I will get some number of things from some number of classes. I don't know what they are. Right? I can't do few shot learning because I don't know what K and N are. Right? I can't cluster and say I want K clusters. Right? I got to fix it. So in this work, we're going to assume the closest we could find was at the time is an algorithm called Finch. Came out in CVPR 17, which is parameter free. It produces a bunch of partitions. So it comes up with its own set of, these are the possible good clusters. And then we just take the finest of those and we use that. But one of the things we quickly learned, and why just clustering didn't work, is impurities in your clusters, especially the early clusters, because I'm going to take what I don't know, I'm going to build a new class, and then I'm going to do this again. Oops, I'm going to do it again. And when I do it again, all those impurities find more friends and bring them into the cluster. And then your cluster just becomes clustered with other random stuff brought in. And pretty quickly, you don't have a good class. So that's a problem, and we're gonna have to introduce a new way of addressing that problem. And then the other problem is we kept it getting beaten up when we tried to publish this because there's no algorithm that does this well. Current state-of-the-art OOD isn't really well suited to incremental learning. And state-of-the-art incremental learning doesn't really solve the open world problem. So we'll have to do some quick extensions to make those things work. Okay, so this is a really ugly and complicated drawing. I'm going to spend the next 20 minutes going over. No, just joking. I will briefly run over this. This is actually from a different one of our papers that's on archive. This is actually the drawing from the supervised version of how to do some of this problem. But it's complicated because I have to take my initial data. I'm going to have some open world system machine that's going to work. I'm going to decide what's known and unknown. And now I'm going to take what's detected as unknown, stick it up into my system. So now I have a buffer. I'm going to somehow go get some annotator to label those, give me the real data. Now I'm going to build a new machine. But everything that happens after this now depends on the result of that first step. Because if I try and compare two machines, A and B, this detects 1, 2, and 3. This gets 3, 4, and 5, right? After this, the machines are diverted. So it's very expensive to run because every time you want to run an algorithm, you got to run everybody through each step, and it gets the errors propagate. But then I can go through. So, and then I want to measure things like what is the unknown detection, the classification, and I have to keep track of all of that for each of the stages. Now, for this paper, of course, we're going to replace the human labels with I'm going to cluster. And I'm going to add this management of what to learn. We'll come back and show you why that was important and what we have to do. So it's a sort of, when Tom was talking, asked like, why you're still working with CFR 10, or it's like, I've learned my lesson. I don't do these things on small problems anymore because it's easy to convince yourself you have something that works when there's only 10 classes. It doesn't work at all when you get to 1,000. So all of these, we're starting with pre-trained networks in general for a full ImageNet 1000. And then we have 166 classes. And these are difficult. We're not like using random things that are nothing like ImageNet because they're much easier. These are 166 classes that were from ImageNet 2010 that were dropped in 2012. So these are things that are pretty close. They're really ugly to deal with and make our problem much more interesting. So those are unknowns. And then we're going to go through a bunch of experiments. I'll come back to this. But we also want to understand the complexities of this problem is how many unknowns do I add? So we're going to have the first one we'll call U5 and often just call 5. We're going to have 5 unknown classes where each unknown has 500 images. We're going to try and keep this balanced. So all of the different tests have 2,500 knowns and 2,500 unknowns, right? And then we just sort of sample from them. So we're not adding another level of imbalance to what's going on. But as we change the number of classes, then the number of images you draw from gets to be different. So when I get to 50 unknowns, now I only get 50 samples from them, and I have 50 classes, so I have a lot more classes to learn, a lot less data. So 2 things are happening simultaneously on that dimension, making it a little bit more complicated. Not sure this is the best protocol, but we came up with something to try to measure multiple dimensions and get it going. And then we're going to run each test 5 times because the randomness in this is really important. The order in which I see images affects what I cluster, which affects what I learn. And the classes I draw from, right, change in each because of the order they're coming from. It's not even like I'm seeing instances. I'm seeing different classes. The first batch of 100 in here may see none of 2 of the 3 classes. So it's much harder to see what's going to happen in the learning. I'm not even sure if 5 was enough, but we did pretty good to show that this was statistically significantly better. So the next issue we had was that we wanted to make sure we understood how do we measure performance when we don't have labels. And so, of course, we have ground truth labels. And so we're going to use those, and we'll talk about why that's problematic at the end, but we're going to use those for now. So we're going to use the normal concept of accuracy for the knowns. So we can say how well did we do in each of our classes as we define in terms of knowns. But for the unknowns, which we just cluster, we're going to use a metric called B3, B cubed F measure, or B3. We also started with NMI, and we learned very quickly that NMI just likes you to over cluster and make lots of little things. It didn't really work out so well. B cubed is a closer measure to which you want to have accuracy. And then we normalize by all the samples. So this gives us a nice measure for how well are we doing that combines accuracy on knowns and a clustering measure on unknowns. Okay. And with this, we get some interesting, Mohsen, are you supposed to be going now? Did I take over?
Yes.
Sorry, Mohsen, please. Sorry about that. You should have jumped in and interrupted me.
Okay, in the bottom picture, you see the first.
Yes,
It is increasing.
Can you hear me?
We can.
Okay. The bottom picture is the first version of the algorithm that doesn't have a management, that we show that in the next slide why we need the management. As you see in the left-hand side, it is closed word and all images is known. So the metric is high. And when we add the novel images or new images that is not in the training in the open set, the performance metric is dropped. And when we go to the open world learning, especially when we have the label and it is showed with the dash line, it's improved over time. But when we using the without label, just clustering without any management, it's not learned much. It's a little, it's negligible. So we can say that it fails. Next slide, please. And if we have some better clustering or a good easy test, we can learn something, but it still is lower than the original closed set. And the reason is that the algorithm find a new cluster that is not matched with the human label. Can you show next? Okay, for example, if you see the following 4 block, it is the 4 clusters that the algorithm show, but as you see, it is for human. When we look at it, it is a good clusters, but it is not matched with the actual label of the ImageNet. For example, we can, after that, we call it the yellow leaves, tree tops, tree trunks, and feature leaf. But because it's not matched, we drop the accuracy in the open word metric. So open word metric itself is not sufficient, and we need to do the human labeling for each cluster and then use the feature, the open word metric. Next slide. Okay, in addition to the metric, there is some issue, as Dr. Bolt said, that some image, when we have the clusters, some, because it uses the nearest neighbor, some image from the other classes show up to existing classes, that here we showed with the red circles, and this red circles in the future cause that we absorb the more feature image like that one, or image between the majority and this image that has, we name it as a cascaded error, and it is very bad for the open world learning without label that we should address. One things that we get that for finding the entropy of each clusters. Next slide. As you see in this slide, we plot the entropy against the variance from the center in Euclidean and the cosine space. As the variance increase, the entropy also increase. The lower entropy is better, it means pure. If it is 0, it means that it's matched with the human label, and if it is higher than, it means that very bad. So we can train the linear classifier like a linear SCM and to reject the classes with the high variance. And as you see, there is a relation between entropy and the variance, is not the causation. So we can select the top one or top n point, and or top point means that minimum point in the entropy in the validation, and use it to train the SVM as a positive and the other as a negative to reject the classes. In the next slide, we have the images of when we use the 2 positive points and the 5 positives, and it is the result of the images. As you see, it is better than without management and just adding any time, because the SCM rejects some of them, but still we have bad images that show in the other hand. And if we use a lower point, for example, 2 or 1, we reject more and we have less number of clusters. But if we have used the more image points like a 5, we get more images, but it's not pure like that. Even with 1 images, we have some bad clusters because it is not matched with the human label, that which cluster is good or bad, it's up to you, and we need to study more in the future. Next slide also show the same result, same algorithm with the different test data, and we see the same result. The left side is the using the 5 image point clusters as positive, and right side as a 2 point. As you see, the 2 point is more pure, but it still is not perfect and need to more study. Next slide. And as Dr. Bolt mentioned, that the out of distribution is not incremental learning, and the incremental learning is not open world. So we extend the past work in the incremental learning to make it the open world learning. There are 3 popular algorithms that use the fixed feature, like a nearest classifier means, centroid-based concept learning, and a scaling incremental learning scales. These 3 algorithms has an unbounded open set risk, and also has a singularity when the number of classes is less than 3. So we fix that, and we call it the ONCM, OCBCL, and OScales. And NNO that Dr. Bolt described in the past slides has the same singularity, but doesn't have the risk bounded. So it is easy fix, and we call it ONNO. Extreme value machine, that was the previous state of the art of the open world learning, also has a singularity issue when we have the less than 3 classes in the beginning, and also it has a problem of the under generalization or over generalization based on the number of the data. So we fix that, and we propose 2 versions of that one, that is the LC EVM that is use the linear classifier for knowns, and EVM for unknowns, and FEVM that use the EVM for both knowns and unknowns. And both version of the LCVM and FEM has a normalization with the L1 normalization to fix some problem and detect as an unknowns. Next slides. So because we are over the time, I skip this slide, that is the details of the algorithms, and you can read it, this algorithm in the paper, and Dr. Bolt continue from the next slide and explain that.
Okay, so the EVM is a core of the best of the algorithms we're going to talk about. It was actually one of my PhD students has been convincing me that we should drop the EVM because it's not the right thing to do. It's not the best open set detector, but it wasn't designed to be the best open set detector. It was designed to solve the problem in open worlds, which means incremental learning classes, which it still does pretty well. We'll see. So EVM is basically a core theory we have from a couple of years ago that is based on the idea that if I look at the distances between things, extreme value theory says that the distribution of extreme values, the closest points to me, right, always follow, they either don't have a distribution at all, or they follow one of a fixed set of distributions. And if it's bounded from below, like distances is, then it's always a Bible. So we use that to say that the distances of the classes approaching my class, the unknown classes or the other classes approaching me, have a bounded distance that allows us to get this idea of the Bible fit. And then we keep a couple of those, we call them the extreme vectors, to keep track of this, right? So this is a very generalized theory of, in any of these spaces, the points will follow this distribution. But it is asymptotic. We have to have enough data and it has to fit. To add a class, all we actually have to do is go by and find all the new pairwise distances of that new data to the other classes. We fit the k nearest negatives, which is again the Bible process, and then we add a couple new extreme vectors. So it's a little bit like when if you've looked at incremental stuff, you know, prototypical vectors, right? The difference is we don't have one prototype per class. We have as many extreme vectors as it is needed to represent this class. And there's a theory that says how I choose the boundary, the distance between the neighbors, as opposed to just saying, I'm going to put some fixed size out there. And then for evaluation, we just basically take the extreme vectors, we figure out the max probabilities, and we can use that to get all of our class probabilities, including all the incremental added classes. So it's relatively straightforward. Getting the pairwise distances in the beginning and do the first fitting is expensive, but after that, it's pretty reasonable to do. as most mentioned, right, we're going to have a bunch of comparisons, but when we get into these comparisons, we want to do a very thorough job. This is actually a journal paper, not a conference paper. So we have softmax rejection, energy rejection, and EVM-based rejection for how do I do out-of-distribution detection. Then we're going to have either for the known classes, do I use a linear classifier or do I use an EVM? And you'll see EVM is not as good a linear classifier for lots of stuff. We're going to use clustering quasi-labels. We've actually been working on our own clustering algorithms, but this paper is going to focus just on Finch, or does focus on just on Finch. We have to decide whether to learn and when to learn, and we have none using the SVM with 2 and 5. We have other choices, but we're just going to use those. And then for the incremental learning comparison, we're going to do the ONNO, OSCM, OSIBL, and OSCAL. And then we also have GMMs, because GMMs are naturally scalable, so we already stuck those in as well. Again, the experiments, I already mentioned all of this. The one thing that we're going to add now that I didn't mention before is we're also looking at do self-supervised features matter, which is another area of interest for many people. So we're going to have supervised features with an S. I means they were trained with MoCo v2 on ImageNet 2012, and then P is MoCo v2 on places, and then we'll look at various combinations of those. So these plots are going to get complicated really fast as we have all that stuff to combine. But this is what we call the true open world comparison experiment, where we have 5, 10, 25, and 50 classes, right? Which means different amounts of data going through those. And we're going to look, in this case, just at the S plus P features. Supervised features trained on the original ImageNet plus places self-supervised feature. And we're combining those. And so here we have the core algorithms across the bottom, and the LCVM and EVM are the gray and green on the right-hand side. The green bars in the first 2 experiments with only 5 and 10 are statistically significantly better. Right? We did pairwise Wilcoxon test and t-test, or I think we did T's on these, but those are significant. The other differences are not significant. So when we get to 25 and 50, the differences are just not, there's so much variation, there's not enough going on there to capture it. When you start sampling from smaller number of classes, you get greater variance as well, right? So the bars here, they don't really look that much bigger, but they're big, they're enough variance. I guess these are pretty big. So out of this, we conclude that out of this set of things, the true winner was FEVM. It was the only one statistically significantly better. We actually know that the OGMMs were statistically significantly worse, but that's not our real interest here. So the next question was, how much does management matter? So in this slide, again, it's too fast to go through these tables in the paper, but to give you a generalized feel, the things that are patterned. So the sort of green checker box here and the tighter green checker box there. Those are 2 managed algorithms. That in fact, the tau EVM and tau LCVM, the sort of results, stick them in the system and manage. We still have to go through the clustering process. And you'll see that in 5 and 10, these differences fundamental learning and the Fitch in terms of what's going on, with no filtering, actually does better when you get to 50. And our rationale for this, we have to do more experiments eventually to prove that hypothesis, is that what the SVMs slow down the learning. You're saying, I'm not going to learn until I get a good enough number of points with a good enough quality of cluster. And so they just don't learn very fast. And when you're in the 50 case, you're only getting a few images so it takes you a long time. So you simply don't learn enough to get good accuracy. Whereas the people who are just tossing them in are getting enough out of it, right? There's still, all of these are way worse than any of the 5s or 10s, right? But management probably needs a different management algorithm when you get to a very large number of classes, and we didn't actually develop them. So the last part we looked at here was, how much does your self-supervised features buy you, and how much your supervised features buy you? So So in this case, the sort of red striped ones of different stripe orientations are with absolute ground truth labels during learning. So instead of doing, this is now open set plus incremental, which is our original paper, right? Because everybody gets all the labels all the time. When they ask for something, they get the ground truth label. Forget the cluster labels, you use the real labels. That provides an upper bound. You still have to detect it, but now you're getting real labels, not cluster labels. The green striped stuff on the left of each sort of subset of stuff is no adaptation. That is, you don't learn. You start from someplace and that's just where you keep going. And then the other three are SVMs, with no adaptation, with no management is the tan colors. Oops, go back. Grays are with SVM1, so the simplest level, and then with SVM5 is the blue, the cyan colors. And I can look at, so now there's a lot to parse through this, but if I look here, I can look at, so pure supervised features, right? Even with pure labels, moving forward, I guess I have to stop pushing. Even with pure labels, self-supervised features improved. The SI and SP are above S, right, as we go across that. So they're slightly above 70, it's slightly below, right? The self-supervised features happen to help with labels. They happen to help even more without labels. So the clustering stuff does even better when it gets to self-supervised features. And our intuition is that what's happening is the feature spaces sort of fold on top of each other. We saw this before in our NERPS 2018 paper. When I've fit to a set of feature spaces, I've designed it to separate those classes. When new classes come along, it may or may not separate them. The self-supervised features were not overfit to a particular set of data. And so they add information that may actually separate things that would have overlapped. And so they provide a little bit, and in clustering that was able for it to be used to get added performance. We did find that the self-supervised ImageNet features, right, don't help as much as the self-supervised places, even though the size of the feature vector is the same in multiple V2 features. And combining all three didn't really add much more. And that's not necessarily surprising because the supervised features are from ImageNet. So adding the self-supervised features to ImageNet helped a little bit, but not much, not as much as adding something that was a little bit more different. Just using self-supervised features for these problems, so just using I or P or I plus P was nowhere near as good as having the supervised features. The supervised features still really help in this class of problems in this high dimensional space. So as Mohsen mentioned, as we were looking at this problem, one of the things we quickly realized that we started out with this idea of a good metric, and it's not a bad metric, but it's also not really about what's going on. So he mentioned these images, right? So think about this. How would you, we gave you our possible labels, but what are you per image labels? What do you think these things are? Okay, so here's the ground truth labels. This is a white birch tree. That's a white birch tree. That's a cork oak. These are coke trees. These are another white birch tree, right? And then these are just trunks of gray, white, yellow birch, cork, right? Visually, they're clustered based on visually similar features, which naturally what you expect for a substance that's using visual features and clustering. But they don't necessarily match labels because no one said, what do you want? Do you want things that look the same? Do you think that they're the same genus? Like the system has no way of knowing what you really wanted out of the system. What is your ideal goal? In fact, if I ask humans how to cluster these images, I'm not sure what our answer. We're going to do some, working on getting human labels so we answer this question. But when I start doing unsupervised learning with unlabeled data, the question is, what label should I give it? Right? Should I talk about tree trunks versus tree leaves, or should I talk about the type of tree it is? And the answer to that is, it depends on who you are and what you want to do with them. Right? And so we don't know, we don't have a great answer what that's going to be. We need better ways or better metrics that somehow match the goals. Because if you want a goal and you don't tell it to me, I'm not likely to learn it. Right? We will learn whatever the data tells us. And if the most prominent thing is actually these visual differences, then that's what it's going to learn. So we're sort of stuck with open world learning without labels, that we will learn what the data distribution tells us, not what labels you wanted. And that's still an unsolved problem. And Dr. Yu's talk was sort of interesting as they're looking at trying to do all this stuff from unsupervised or self-supervised data, we have to be very careful. What is it we want it to learn? Because the distribution of the data might be what we're learning, which is not necessary. And we can make the distribution to the right things by choosing how to structure it, right? Maybe the reason that, if I use all of YouTube, I learned to recognize cats is an artifact of YouTube, or at least the way YouTube was. So at that point, I'll stop and take questions, and I will again mention that I'm looking for postdocs. So looking for postdocs. Questions, comments?
So instead of like hardly assign the novel sample simple cluster, is it better to just have like soft assignment with some probability? And what's your criteria for creating a new cluster?
So the question was, we did hard assignment of points into clusters. Would it be better to have soft assignments? And what was our criteria? And so the answer is probably yes, it would be better. We have probabilities. But if we want to use them in the next round of clustering, right, and I have to decide, are they known or unknown to what class they're in, I have to give them a probability. So eventually we have to make some hard decisions at the evaluation stage. But a soft classifier might be a better approach. We just did not pursue it. And then right now, the way we're clustering them, so Finch is a first nearest neighbor classifier. So it uses the nearest neighbors to cluster them. And then we evaluate that cluster using the SVM that was trained on the validation data. So we had some validation data we got to use. And that decides whether or not the cluster is acceptable. And once it's acceptable, we take its labels and we then use it as hard labels in our labeling process. So if we wanted to do soft labels, we'd have to both make that process give us soft labels and then use multiple probabilities to learn from. But it's a good direction to go. Other questions? Questions on Zoom? Okay.
Thank you, Derek. Thank you everyone for attending our workshop. I hope you had a great time. I hope this workshop leads to many more questions and more interest in this area of vision and machine learning. Thank you everyone.
No.
Okay,
Not-
cancel.
Too late for people on the East Coast, I think.
Oh, yeah.
Oh, I see some chats.
Yeah, I was in the remote biometrics workshop, and like it's being run by like people in Portugal. Like, yeah. Poor guy. It's rough. It's like,
At least it's not rough as the rest of the conference, which starts at 1 p.m. here.
yeah, man. When we moved to like, especially like CDK, like the 24-hour format, that was a huge mistake.
Oh, completely. Like I had, like no one would go to both sessions. Like it just
So thanks, Mohsen. Good job.